Well, thank you very much to everyone. And I think we can more or less have a look at the schedule. We'll start with Saravya, who will give a general talk to introduce the topics of type 1a supernova, the different aspects of progenitors and explosions and observations. Then we'll follow with Fritz, with multidimensional simulations of type 1a supernova, with Ken Shen, with type 1a supernova from double detonations emerging double white dwarf systems, the D6 scenario, and then we'll have a coffee break. So after the coffee break, we will present the rest of the program. So Sarav, if you are around, you can start sharing your screen.
Pilar, it says you have to stop sharing before.
Yeah, I stopped.
Okay, can you see my slides?
Yeah.
Okay, well, thank you everyone for coming, and thank you for the organizers for the invitation. Yeah, as Pilar said, I'm gonna try and give an overview of basically what's gonna be discussed over the next two sessions. So I called the talk here, Type 1a Supernovae, Astrophysics and Cosmology. So today I think is gonna be more on the astrophysics side, and then on Thursday is more on the cosmology side, but I will try and hit both of those as I go through. So basically, I want to talk a little bit about just what are the objects that we're discussing, what's the physics behind them, and then why, of course, they're important when we use them as tools for cosmology. So I like to think of it more broadly than just type 1a supernovae. So I like to call them either white dwarf supernovae or thermonuclear supernovae, and either the thing that is exploding, i.e. a white dwarf, or the energy source for the explosion, thermonuclear fusion. And I should say that there's limited direct evidence that these objects that we think are white dwarf supernovae are really exploding white dwarfs. So what you can see here are two figures, one showing a limit on the radius of the exploding star from the very early light curve of 2011 FE, which suggests that the star was quite small, maybe a 50th the radius of the sun, so very consistent with being a white dwarf. And then here is gamma ray emission showing what's purported to be the decay, the radioactive elements that are being produced in the explosion. So I would say those two pieces of evidence are sort of getting at directly probing that this is a white dwarf explosion with thermonuclear fusion as the power source. But of course, we know there's a lot more indirect evidence that points us to this picture. And so basically here you can see, for instance, the spectral homogeneity in all of these objects. They're very similar to each other. So homogeneous spectra with degenerate carbon-oxygen fusion products. The bolometric light curves follow the nickel-56 decay. We don't see massive star progenitors. We don't see compact objects in remnants of white dwarf supernovae. And we do see these objects in older stellar populations. So again, saying that they should not be associated with massive stars. Okay. So all of this is, again, I would say more indirect evidence that we have this right picture, that we have an exploding white dwarf. And I think in an upcoming talk, in Wolfgang Kurtzendorf's talk, he'll look at using the spectral time series, for instance, to explore this question a bit more. But often when people talk about this subject, then they say, okay, we know that there's a white dwarf exploding. And then the question becomes, what is its companion star, right? So that's this idea of whether it's a single or double degenerate system. Is the companion star a main sequence star or a red giant in the single degenerate scenario, or is it another white dwarf in the double degenerate scenario? But I think that we've been pushed into that debate, that dichotomy, and I think it's actually a good idea to step back from that. I think the questions are much larger than that, much broader than that. As I said, what we think we know is that a carbon-oxygen white dwarf is exploding, right? And even then, the direct evidence, as I just said, is somewhat limited. But I think we don't know at what mass, right? So there's this, of course, natural Chandrasekhar mass where you might expect explosions, but we don't know for sure that these explosions are Chandrasekhar mass explosions. We don't know the companion, as we discussed. We don't know the accreted material. For instance, is it hydrogen? Is it helium? Is it carbon oxygen being accreted from 2CO white dwarfs? And then that's in the progenitor system, but then also for the explosion, how does the explosion proceed? Right, so there could be a subsonic deflagration, a supersonic detonation, a transition between the two, a double detonation, right? So all of those questions about how the explosion proceeds, I think, are also open and will be touched on later today. Okay? And then, if there is a companion, what is the interaction signature with the companion? And is anything left behind? So the standard idea is that the white dwarf completely explodes. And so the primary white dwarf, there shouldn't be anything left behind. But do we know that for sure? And then what about the companion star? What's left behind it? So I think those are all the open questions. And I assume that many of them will be touched on today. So I just want to set the stage a little bit as an overview today. Okay, so some interesting observational and recent developments in addressing these questions. So for instance, now that there are these surveys that observe the sky to find new supernovae all the time, we have gotten much better at finding light curves of supernovae at very early times, okay, when maybe the effect of the companion star will be more prominent. And so people have been using telescopes in space like Kepler and TESS to look at these very early time light curves of type 1a supernovae. And you can see that there is some variety of what's going on at early times. So this is kind of a compilation of a few different objects. And you can see that some just rise very slowly. So the dots here, this Kepler supernova, it just has this kind of nice rise. But then here are some other objects which showed some different behavior early on. Okay. For instance, this one, 17 CBV, shows some extra emission early on. This one, 2018 OH, has a little bump here. Okay? And so the question is, what is causing this? One natural idea is that this is the signature of the ejecta from the supernova hitting the companion star. And so you get this extra flux early on. But there may be other explanations. So for instance, if you can get some of the radioactive material further out into the ejecta, then you can get this kind of signature in the light curve as well. So I think this is still uncertain what's going on with these bumps. But I should say that these bumps are not ubiquitous. You can see them sometimes, but not in most cases, you don't see them when you have good data. Okay. If you look at late times or to see is there any indication of that companion star in other observations. So for example, if you are accreting hydrogen or if you ablated hydrogen off of the companion star, if it was a main sequence star or especially a giant, then you might see that hydrogen, especially through H alpha at late times. And there have been a handful of supernovae. There was just one a few days ago on the archive, on this paper here, a handful of supernovae where you can see a signature like that. Okay. But the vast majority here's a compilation, the vast majority do not show signatures like this. And so, this idea of, whether you can hide this material is really the question. Or is it the case that the material is just not there and that's leading you to consider the double degenerate scenario where there's not expected to be any hydrogen really in the system? So lots of interesting questions there. And then I would say that, if taking a broad view on this question, there's more than just type 1a supernovae in exploding white dwarfs. So there's this whole thermonuclear supernova zoo, a nice review article by Stefan Taubenberger. And the question is, all of these other things which are not the normal ones here, but type 1ax supernovae, which I like to study, lots of other classes of these objects, what are they telling us about normal 1as? So I think that's a big open question, and hopefully people will touch on that today as well. Okay, here's another kind of interesting development, I think, and we'll see a lot more in the Abigail Holland's talk later. So I'll just flash this up as an exciting development. This idea of how the explosion proceeds, whether it could be a double detonation, where we have a detonation on the surface that then drives the detonation of the primary white dwarf. That's a really interesting idea. Are there observational signatures of that? In a few cases, it looks like maybe there are, and I'm sure that she'll talk more about these objects later on. And then we also have a talk by Ken Chen coming up, so I had to advertise this great work. Here is the idea of what happens to the companion star. So if the companion star is another white dwarf in the double degenerate scenario, but that companion star survives the explosion, then if it was transferring mass at Roche-Loeb overflow, it would have been moving very quickly right before the explosion. And so those companion stars would get shot out of the system with quite high velocities. And so Ken led this project to search for those using Gaia data. And indeed, we found 3 such potential objects, which could be these surviving companions, white dwarf companions to white dwarfs that exploded as type 1a supernova. And I like to call these fugitive stars because they were the ones that were responsible for donating mass to the exploding white dwarf, and now they are fleeing the scene of the crime. So I'm sure Ken will tell us much more about these. And then there's this possibility, and for these other weird stars that have been discovered in the galaxy, which have these funny nucleosynthetic signatures, these white dwarfs, possibility is that, we said that for a normal type 1a, we expect that the whole white dwarf explodes and is completely disrupted, but that may not be the case, and maybe especially for some of the peculiar kinds, like maybe for type 1ax supernovae, where there's a surviving, some part of that white dwarf survives. And it may have this strange nucleosynthesis because part of the star actually exploded. Some of that material might fall back onto the white dwarf and stay there. And you might see a signature like this, these sort of relatively rapidly moving stars with white dwarfs with unusual abundances. So they may be these partially burnt remnants of a white dwarf supernovae, so maybe related to the type 1ax supernovae. And these were predicted as long as almost a decade ago that these might be seen. Okay, so that a little bit brief overview in terms of the astrophysics, I think, and especially the new developments in the astrophysics of type 1a supernovae. There's a lot more, and we'll hear about nucleosynthesis, I think, in a couple talks, other things like that. So there's all of these constraints on progenitors and explosions, and I think the big challenge is we haven't really been able to take all of these constraints and put them into a simple picture of what's going on. And yet we still want to use these type 1a supernovae to do cosmology. So there's this rich connection between the white dwarf astrophysics, exploding white dwarfs, and the supernovae themselves, the explosions themselves, and then the application to distances and cosmology. So now briefly, I'm going to switch gears and talk about this connection to cosmology, where most of the stuff that in this conference, most of the applications to type 1a cosmology will be discussed on Thursday. So just as a reminder, how we use type 1a supernovae for cosmology, type 1a supernovae are treated as standardizable candles. We make use of the Phillips relation that the light curve decline rate or the light curve shape is correlated with luminosity. And that's what you see on the left panel here. So in the B band, the faster declining objects are less luminous, the slower declining objects are more luminous. And then you can see that in other optical bands. But as you go to longer and longer wavelength, here it is, for instance, in the H band, the Phillips relation becomes pretty flat across here. And so in the near infrared, it looks like the luminosity is fairly standard, not necessarily standardizable. But most of our data, as you can even just see visually from this plot, most of our data is in the optical bands. And right now, basically, we use this, the kind of state of the art is to use this SALT-2 model with the trick standardization, where we measure a peak magnitude, we measure something related to the light curve shape, and we measure a color. Okay? And we make 2 corrections, one for the light curve shape and one for the color. Okay? One thing I want to point out, especially if you work more on the astrophysics side, when people think about this, people think that this Phillips relation is really the dominant source of the correction. But for cosmological samples, we usually limit which objects we look at in this range of light curve decline rate. And in that case, the color correction is actually usually larger on average, or in terms of the range than the light curve shape correction. Okay, so for instance, the light curve shape in the SALT-2 parameterization might be between x1 between -2 and 2. That would lead to about a 3/10 of a magnitude correction on the Hubble diagram. Whereas for the color, if we go from -0.1 to 0.3 magnitudes, roughly in V minus V color, that leads to a larger correction typically. So color is actually the largest correction in supernova cosmology analysis. And this is the range I was talking about of where we try and observe these supernovae. Okay, so applications cosmology, of course, people are familiar with the type 1a supernovae being used to discover the accelerating expansion of the universe and the idea that the universe may be filled with dark energy. So obviously there are many, many projects that have built upon that. And so here's a relatively recent compilation, now a few years old already, of I think it's about 1,200 type 1a supernovae at high redshifts, standardized in this way to show that there is dark energy in the universe is accelerating, And so here are the constraints compared to the original constraints way back from 1998. Okay. And it's important to know that the cosmological applications of supernovae are always a differential measurement. You always look at supernovae somewhere against supernovae somewhere else. And in this case, the differential measurement is between Hubble flow supernovae nearby and then these higher redshift supernovae farther away. If we come even closer, then more recently, the distances to type 1a supernovae have been used to measure the Hubble constant. And of course, you've heard that there's this tension between the Hubble constant measured in the high redshift universe with the CMB and assuming lambda CDM with the local measurements, especially with supernovae and Cepheids. Okay? And there's a lot of, lots of different measurements here. And this is that difference between the CMB type measurements and then local ones. And there's many talks. I think people will talk about this on Thursday. I think it's going to be a roundtable discussion. I think there's a whole separate session in this conference about the Hubble constant. So I won't go into too much detail, but I will say from the supernova point of view, it's very hard for this discrepancy to be explained only by the supernovae. And the reason is that the Hubble flow supernovae are just not that different from the ones that are calibrated with Cepheids or other techniques. Okay? So it's only a factor of, sort of here like 8 in distance. The look back time is not a significant large fraction of the age of the universe. So it's really hard to get something like a 9% systematic effect between very nearby supernovae and Hubble flow supernovae. Okay? And you can also work to make those samples similar on average so that there's not much leverage for any kind of systematic effect to play a role. So, what else could be going on? So for instance, you can see here, using the same kind of supernovae, you can see that there's a difference that you get from the Cepheid calibration and the tip of the red giant calibration. So my feeling is if this tension is going to be explained by systematic effects, I think the larger systematic effects will be on other rungs of the distance ladder, not in the type 1a supernovae. That's just my opinion. There are people looking into what effects in the type 1a supernovae could be important. Here's one. I won't go through all these slides, but the idea that the type 1a supernovae do, after standardization, the distances you get depend a little bit on the host environment, either the host galaxy stellar mass or the star formation rate or the age of the environment. There are indications that all of those things could be contributing, and we are correcting the supernovae differently based on that environment. So I think this is very important, and it could be quite important for future dark energy, precise dark energy studies with type 1a supernovae. But I think the effect on the Hubble constant is relatively minor. At most 2%, but probably closer to 1% effects from environmental systematics like this. I just wanted to highlight my graduate student, Kyle Detman, who's finishing up soon, this paper showing, again, this relationship between an intrinsic parameter of the supernova, the explosion speed, and an extrinsic, the environment, the host galaxy's stellar mass. Okay? And this is independent of any standardization of the 1As. We can see that different kinds of 1As explode in different kinds of galaxies. And if we want to really use 1As to the utmost precision, we need to understand what is causing these kinds of correlations. So that ties the cosmology back to the astrophysics. One little thing I just wanted to put in, one little plug for a project that we're doing with the Hubble Space Telescope is to use, I showed you how in the infrared, the type 1a supernovae are better standard candles. So we've been trying to build up a sample of Hubble flow supernovae type 1as observed with HST in the infrared, where we don't have to worry about the absorption from the Earth's atmosphere. And so we'll do cosmology with this sample, and we'll also use it as a building block for the Roman Space Telescope, which will observe thousands of type 1a supernovae in the infrared in the future. Okay, so I just wanted to summarize with this very, very nice figure from Dan Skolnick in a review paper, and to highlight that on Thursday, we'll hear about supernova cosmology talks that cover this paper. But this is the sort of the future of supernova cosmology, what we'll be able to do with different samples. So very nearby supernovae, we'll be measuring H0, the Hubble flow supernovae, peculiar velocities, H0, but also we'll connect to the higher redshift, okay? And then higher redshift supernovae to do dark energy, lots of different ways that we can attack dark energy from all of these surveys that are coming to find lots of supernovae in the future. So I'm excited for the surveys. I'm excited for the talks later in this session and the talks on Thursday that will cover these cosmological applications. So thanks.
Thank you very much, Saurabh. for this very nice overview. I wonder if there are questions. Please go ahead with the questions.
Fritz is raising his hand.
Actually, I just want to clap. Sorry for that.
Oh.
Yeah.
I have a question. Sarah, how many of these companions of 1AX, of these white dwarfs that are polluted with the products of the explosions have been found? I
I
didn't.
think maybe 3 objects, and I think they're all here. I think these are the 3 in the upper right.
The 3. Oh.
Yeah.
Very interesting.
I mean, it's hard to find, right? So here they are on the HR diagram. So they're faint. They're not quite as faint as normal white dwarfs, but they are faint. And so there's only a certain volume you can see them. So I don't know if people have done the rate calculation to see if this is exactly what you would expect for what we think the 1AX rate is, but whatever these are, they're certainly very interesting stars.
I see Wolfgang is raising his hand.
Yeah, I mean, just a comment on this. I think, like, with these things, we need to be, they are unusual white dwarfs or unusual things. So we don't have a direct link yet. There is a tentative idea that one of them goes back to a supernova remnant. But I think, like, for now, we just think they're unusual stars. I mean, if this is correct, Saurabh and I are both co-authors of the study.
So I do want to specify the difference between these 3 stars, which are the fugitive stars, and then these 3 stars, which are different. Yeah. And I think I put enough question marks on the slide to say, yes, we don't know.
No, you did.
But they have also hypervelocities, these ones?
Yeah, they're not quite as fast, but they are a few hundred kilometers per second, yeah, as the other ones.
Okay, very interesting.
Can you go back to the, sorry, this is Ken. Maybe I should raise my hand. I'm raising my hand, but you can't see me. Can you go back to the slide of your, with the Detman results? I was just wondering, so you're seeing the velocities, the silicon velocities there's a faster group in the higher mass population. Is that right?
Right.
I was wondering, do you have the magnitudes as well, like the absolute magnitudes? So those are presumably brighter explosions.
Yeah, so that would, let's see if we can, so it would be here, this plot should show you that, at least not with the X1, the light curve shape is probably the better thing to correlate against that. And actually you can see that the ones up here, which with the higher velocities, they span a range of X1. There are a few which are on the low side. So it's not, yeah, it's not exactly the same. I would say the thing that is striking to us, and other people have pointed this out, is that it does seem to be for these low mass hosts, which all have relatively normal velocities. There's this kind of so here again they're down here. They have a relatively narrow range of X1 light curve shaped behavior, and they have a narrow range of color. And so this is a very promising place. So there's a paper by Dylan Brout and Dan Skolnick that points out these objects, and other papers. I think this is a promising place to look at. Perhaps what's going on there is that these are the youngest 1As, right, in these very highly star-forming low mass galaxies. And perhaps the youngest 1As are basically the same no matter where you observe them in the universe, and they seem to have these specific properties: low velocity, somewhat overluminous, somewhat broader light curve shaped, and then blue colors. And so that might be a promising avenue to kind of hone in on those objects as more standard candles for the future.
I can't do the convert. I'm not used to that. I'm not used to SALT 2 X1. How bright is a typical -2? Yeah,
so the alpha, which you multiply, is 0.14. So -2 would be 0.3 magnitudes fainter, and +2 would be 0.3 magnitudes brighter.
Okay. So these aren't like, there's nothing here that's like subluminous. There's no.
So again, because we focused on the cosmological ones here. Yeah, exactly. It's you know,
Okay. I don't see any other hand raised. So we move to the next talk. So Fritz.
Yes, so I'm going to share my screen. Let me just quickly go here and start the presentation here.
Very nice.
Okay, can you see my slide here?
Yeah. Mm-hmm.
Okay. All right. So I would also like to first thank Pilar and Robert for organizing this. It's great to have a supernova meeting. Actually, there has been quite a while now. So I'm going to talk about multidimensional simulations of thermonuclear supernova. I just switched the title of the Sorry, there any? Okay, there was somebody talking. Okay. I just switched the title from Taiwanese supernova after a suggestion, which I liked, and changed it to thermonuclear supernova. I will focus on simulations of the explosion stage itself, and not actually say much about progenitors here. So my work that I'm going to present was carried out in a large collaboration. I would like to highlight in particular the contribution of my PhD students, Sabrina Grono and Florian Lach, and also that of our collaborators in Belfast, Christine Collins, Fintan Callan, and Stuart Sim. Now, setting aside problems of the progenitor scenario, for setting up an explosion model, the most important question, of course, as you all know, is the state of the white dwarf it is in when it starts the explosion. So is it close to the Chandrasekhar mass or not? And if it's close to the Chandrasekhar mass, then its density structure is, as shown here, it's a very compact structure. So most of the mass, most of the material is above 10 to the 7th grams per cubed centimeters. So that means if it's overrun by a supersonic detonation, it will be turned entirely into nickel and iron, which is inconsistent with the observations of Taiwanese supernova. We know that intermediate mass elements have to be produced, and for that, burning at lower densities is needed. So we need to pre-expand the star before it gets burned, and that's possible if the burning takes place as a subsonic deflagration. Now, these deflagration models of white dwarf explosions at the Chandrasekhar mass have been studied quite extensively in multidimensional simulations by many groups in the last 1 or 2 decades. Here's one example from our group. So this is the Chandrasekhar mass carbon-oxygen white dwarf that is ignited near the center in a number of ignition sparks. Then the flame propagates outwards. The subsonic deflagration flame is subject to buoyancy instabilities. Secondary shear instabilities give rise to turbulence that interacts with the flame, accelerates the burning, and in the end, the flame propagates through the white dwarf star. The strength of the explosion and its ability to completely disrupt the white dwarf depends on the initial parameters in these models. So all the effort that we put into constructing multidimensional simulations here was in order to avoid tunable parameters in describing the burning physics itself. But of course, we have initial parameters. And these initial parameters dominate and decide on the strengths of the explosion. And the secondary parameters are the density, the central density of the white dwarf at the onset of the explosion, or its composition. The primary parameter is the way the flame ignites. And these parameters, of course, all connect to the progenitor evolution, but the exact connection is very hard to model, in particular in multidimensional simulations. So the best we have on the ignition process itself in multi-D is the simulations by the Stony Brook group, and they actually find that a single spark ignition off center is the most likely case. Now we have taken the ignition configuration as a free parameter in a sequence of models that you see here, and we have distributed different numbers of ignition sparks around the center of the white dwarf star. And if we choose many ignition sparks, of course, we can distribute them in a rather symmetric way. And then we obtain models that produce rather strong explosions. So here's the ejected mass, and in this case of many ignition sparks, the entire white dwarf gets unbound. However, if the ignition proceeds only in few sparks, then the deflagration will propagate in a very asymmetric way, will not reach all the material, and therefore the explosion is weak. It expels only a fraction of the white dwarf, and a bound remnant is left behind. The other interesting property of such kind of models that's seen from this plot here is the mass of nickel 56 produced in these models. And it always stays below the canonical 0.5, 0.6 solar masses that we need to explain the brightness of normal type 1a supernovae. So these are models only for subluminous events, and indeed they have been associated with objects such as supernova 2002 CX, which then later was interpreted as being at the right end of a larger distribution of objects inside the class of type 1ax supernova. Now this leaves the question open whether with the Chandrasekhar mass deflagration models we are able to also reach down to the very faint objects in this class, supernova 08HA for instance, and whether we can actually reproduce its properties as well. And in order to explore this, my student Florian Nach has set up a set of simulations where he followed a single spark ignition scenario based on the results of the Stony Brook group. And he varied the distance of the ignition spark from the center of the star, but also other parameters such as the center density at ignition, metallicity, the rate of rigid rotation, carbon mass fraction. So in total, he computed 30 models. And the goal of this was to populate the fainter end of the distribution. So what you see here in this plot is the nickel 56 mass over the ejecta mass of some of the objects that have been observed here in orange, and the models that are available at the moment cluster around the brighter end of that distribution, and our goal was to populate the faint end. And here Florian now has added 30 new models, and indeed with these it is possible to reach down to rather low nickel 56 masses in the ejecta, 0.06 solar masses, but even lower nickel 56 masses seem to be possible. The other result is that the kick velocities can vary quite a bit. The kick velocity is imparted on the bound remnant. So this here shows how the deflagration ashes rise towards the surface of the white dwarf. They break out of the bound white dwarf and sweep around it. And if they manage to close up on the far side, then the kick is imparted onto the bound remnant into this direction. If they don't close up, then it's imparted to the other direction. So that means that for these bound remnants, absolute velocities that potentially could be measured are possible in between 0 and a few hundred kilometers per second. The other property of these models that you see from this plot is that there seems to be a rather strong correlation between the nickel 56 mass and the ejecta mass. And this is actually obvious here, but it misses the observed objects. Now that could be a problem for these models. Now let's look into what predicted observables tell us. These were computed by our colleagues in Belfast. We actually reached volumetric peak brightnesses very far down to minus 14.91 magnitudes. The brighter models agree reasonably well with the observations in terms of spectra and light curves, but the fainter ones do not agree so well. And the strong correlation between the nickel 56 mass and the ejecta mass actually leads to light curves of the fainter events that evolve too fast compared to the observation. That's shown here in this with luminosity plot. So we have the fainter type 1a axis here, and our models always fall above that range and parameter space. Now, as I said in the beginning, we have actually tried to break that strong correlation with testing other initial parameters, central density, metallicity, and so on, but it's very hard to break that correlation between nickel 56 mass and ejecta mass that gives rise to this mismatch with the observations. Now, it could still be that we have shortcomings in the radiation transfer modeling. The Belfast group has recently implemented a better treatment of non-LTE effects in the ARTIS code, but this still has to apply to our models. What we also left out is contributions to the emission of the bound remnant, which in particular may be important for the fainter events in late epochs of the observation. But it's also possible that the faint end of the type 1a axis has to be explained by a different explosion scenario. And there are some hints for that. For instance, the stratified ejector composition in the outer layers that is found by abundance tomography carried out by Max Stritzinger and Barnabas Barna. And for some of the faint objects, even if a completely different explosion scenario, the core collapse origin has been discussed. Now, the next logical step discussing multi-D explosion models would be now to switch to delayed detonations of Chandrasekhar mass, white dwarfs. We're working on some new models, but there's nothing to report yet. So therefore, I will skip this and rather switch to sub-Chandrasekhar mass explosion models. Now, these sub-Chandrasekhar mass white dwarfs are, of course, less compact, and therefore, even a detonation can produce intermediate mass elements, in principle, produce objects that could look like normal type 1a supernovae. And this actually has been tested a long time ago together with Stuart Zim, where we set up toy models, sub-Chandrasekhar mass, bare carbon oxygen white dwarfs that were artificially ignited as a detonation at the center. And these objects looked similar to normal type 1a supernovae, and with varying the mass of the exploding white dwarf, it's even possible to reproduce at least the trend of the visible luminosity relation. And Ken Chen has put much work into more sophisticated models with improved nuclear synthesis treatment and also radiative transport calculations, and he finds a nice match with some observations. And I'm sure he will talk about this. Now, the question for the sub-Chandrasekhar mass explosion models is how to trigger the detonation in the first place. And of course, again, this relates to the progenitor evolution. Is it a dynamical phenomenon in the interaction of a double degenerate system? Is that more classical accretion in a single degenerate system? I will actually now turn to a more generic point of view. In all these cases, the explosion mechanism involves a layer of helium-rich material that is accumulated on top of a carbon oxygen core. It undergoes a detonation, drives a shockwave into the core, and then sets off a secondary detonation there. Now, these models have been discussed as candidates for explaining normal type 1a supernova. From our toy models with pure carbon oxygen sub-Chandrasekhar mass white dwarfs, we know that such a scenario can actually cover the brightness of type 1a supernova by changing the mass of the exploding white dwarf star rather easily. And these models would probably also follow the observed correlations. However, if we now enter at the helium shell detonation, we run into problems because the helium shell detonation ashes shift the flux towards the red, and then the predicted spectra don't agree with the observations. That's why a lot of work was put into minimizing the effect of the helium shell detonation ashes by reducing the mass of the helium shell or introducing some mixing between shell and core. And recently, Dean Townsley drove this to the extreme, and at least for some viewing angles of his explosion models, there's a nice agreement then with observed spectra, as you see here on the right-hand side. Now, all this illustrates that the helium shell detonation is critical, and therefore we recently improved our previous treatment with Levisets, which is rather parameterized and not very precise, to using a new numerical scheme, the RAPO code. And this led to models that my student Sabrina Grono recently published. So here's one example. You see the helium shell detonation sweeping around the carbon oxygen core and colliding on the far side. It there produces a hotspot where a secondary carbon oxygen core detonation is set off and explodes the core. Now, with varying the parameters, the core mass and the shell mass, Sabrina created 13 models. She finds different mechanisms for igniting the core detonation. So that seems to be a rather robust process. However, all models, even those with rather thin helium shells, still are too red compared to the observations because of the helium shell detonation ashes. This may be due to shortcomings in radiative transfer. Again, non-LTE effects, as recently introduced in the artist code, lead to quite a change here, but this is still something that is under investigation. So Christine Collins is looking into these effects and needs to still determine how much of a change we can expect here. But there's also other problems with this model. And this is actually with these multidimensional simulations, we actually find a rather strong viewing angle effect. And this is actually illustrated here in this bolometric with luminosity relation that was put forward by Richard Scalzo. Our angle average models actually fall into the parameter range of that with luminosity relation. But if you look into these bands, these color bands that actually illustrate the viewing angle effects, they actually introduce a too wide spread. Another problem is that the decline rate of the bolometric light curves after 40 days in our models is way too quick. And this may actually point to problems with the gamma ray opacities, maybe with the masses of the ejecta and the velocities, rather independent of the treatment of the radiative transfer. So these may point to some generic problems of such models. And a similar argument was recently also made by Doron Kushner. Now, finally, I would like to quickly discuss some imprints on nucleosynthesis of different explosion models. I will just discuss one argument that we made a while ago together with Ivo Seitenzahn. So the idea is the following, that in thermonuclear supernova explosions, iron group elements are produced either in incomplete silicon burning or in normal freeze-out from nuclear statistical equilibrium or in alpha-rich freeze-out from NEC. And that depends on the density and the temperature that's reached in the burning region. And for Chandrasekhar mass deflagrations, the nickel 56 that's color-coded here is produced mainly in normal freeze-out from nuclear statistical equilibrium. There's some contribution from alpha-rich freeze-out and incomplete silicon burning. Now, the argument to distinguish between different models is based on the manganese production. Manganese is produced by cobalt-55 decay, and cobalt-55 is synthesized in these Chandrasekhar mass explosions, mostly in normal freeze-out from NSE, with some contribution from incomplete silicon burning. However, in alpha-rich freeze-out, no cobalt-55 is produced because it gets destroyed by the abundant light particles there. Now, taking a 1D detonation of a sub-Chandrasekhar mass white dwarf is here, we see that there's little production of cobalt-55 and ultimately manganese. There's some, it's hard to see here in this plot, from incomplete silicon burning, but the conditions do not reach normal freeze-out from NSE and only some incomplete average freeze-out from NSE, and here no contribution to the manganese is obtained, and therefore these models lead to subsolar manganese over iron ratios. Now we know that we need type 1a supernova to drive the galactic chemical evolution of manganese over iron to the solar value, and therefore the argument has been made that we need Chandrasekhar mass explosions for that. However, if we now add the helium shell detonation to this model, then we see that we have another side of producing manganese or cobalt-55 and ultimately manganese. And in these models, it is possible to produce solar or supersolar manganese over iron ratios. And we have put this into GCE models together with Benoit Coté and the metallicity dependent yields that Sabrina Grono has recently published of her double detonation sub-Chandrasekhar mass models are taken here as the only contribution from type 1a supernovae. And you see that with these, we can actually reproduce the observed trend and even the final solar manganese over iron ratio. So we need very little contribution of Chandrasekhar mass white dwarfs, provided that for core collapse supernovae, we take the Demonge and Chaffee yields with the yields of Kanemoto and his group, then there's less contribution of core collapse supernova, and then in this case we need also a substantial contribution of Chandrasekhar mass white dwarf. But overall, this production of manganese in the helium shell detonation now weakens the old argument that we necessarily need a strong contribution of Chandrasekhar mass explosions to explain the manganese over iron ratio in the sun. With this, I would like to put up my conclusion slide, show the multidimensional modeling pipeline that is used to derive some constraints on the explosion scenarios. I didn't have time to talk about some other things such as polarization or the morphology of the remnant predicted from such models, but I've put up the references to this here. With this, I would like to stop and thank you for your attention.
Thank you very much, Fritz, for this very wide and very interesting talk. I wonder whether there are already questions in the raised hands. It seems that my facility for seeing the raised hands is not working now.
Ken has a question.
There's a question by whom?
Ken has a
Ken.
Okay.
Thanks, Fritz. So I had a question about the ejecta mass and kick velocities for the 1AX simulations you've been doing. So you mentioned that you find kicks up to a few hundred kilometers a second. Is that right?
Yeah. Let me go back to that slide. Yes, but yes, yeah. 300.
But that's with pretty low ejecta masses, right? And so I was wondering, if I recall correctly, the Fink 2014 results, the kick velocities that you and he found were pretty low, even though the
Yes.
ejecta masses were a lot higher.
Right. I mean, this was actually now done with a better version or an updated version of the code where we actually sort of improved the treatment of the gravity solver, right? So in the Fink models, we had a monopole gravity solver only, and this now actually is an FFT gravity solver. So I would trust these results more than the old Fink models.
Okay, so that's good because we see, if we believe that the results that Roberto already, some of these funny white dwarfs he's found have kick velocities that are of order, 800 kilometers a second. And so if we believe these are from 1AX remnants, that would be nice to, a little more ejecta mass, a little higher ejecta velocities.
Yeah, but I mean, it's not necessarily that they always have very high velocities. I mean, as I've shown, I mean, the kick can go in both directions. So in principle, it's also possible to have very low absolute values of the velocities there. So it's all possible in between 0 and 200.
Thanks.
Fritz, I have a question concerning your first set of models, the ones that could reproduce the 1AX. How
Could or
different?
could not, yes.
Well, or could not.
Yeah.
The treatment you do here is similar to the treatment from that you did for instance for the N100 model. So you spare you give some different points of ignition around the Chandrasekhar white dwarf, and you follow and
Well,
the detonation. Is similar in this sense, or is
it's a deflagration, and actually we use our old code with a level set for describing the turbulent deflagrations. What's different here is actually, as I said, we have done some updates for the gravity solver and some other things in the code. So all these are single spot ignitions. So we do not actually ignite around the center, but only in a single spark that has this sort of shape that's composed of multiple bubbles, but that's only as a numerical kind of thing to invoke some radiator instabilities, because with a single spherical bubble, that's actually an initial setup that is not convergible, because it always depends on your resolution, how you actually break the symmetries then. But in principle, what we try to model here is a single spark off-center ignition with different offsets from the center.
But this single spark you think is a realistic treatment for?
Well, according to the results of Mike Singali and his collaborators, that's the most likely case. Yes, I mean, as much as it is possible to simulate this pre-ignition phase, which is very challenging, very difficult, but that's actually what they find and what they actually sort of claim is the most realistic option.
I think now we have another talk by Ken Shen, or are there more questions for Fritz? Hi Pilar, sorry for the naive question. I suppose now, okay, this is just about time. Yes. No, this is now Central European time. Xin. It's a question by Xin Shi concerning the time. You will be talking very soon after Ken. Oh, sorry, it was private. So now I will follow with Ken because I don't see any more questions. Do you see, Bob, some questions?
No, I think we'll have a lively discussion during the roundtable as well.
Especially, I was thinking in Abigail models that will also show how they look like at late times, all these different kind of sub-Chandra and Chandra models. There will be more discussion on this. Yes, so we now go and shift to Ken's, sharing the screen.
All right. Does that work full screen? Yeah, good. And can you see my cursor?
Yes.
Yes.
Excellent. All right, here's my laser pointer. Hi, thank you very much for the invitation. I'm excited to tell you today about double detonations in general, but also I'll spend the second half of the talk focused on a subset of double detonation type 1a supernovae, in particular double detonations in merging double degenerate systems, what we have started calling the D6 scenario. So first I want to just make a point that Saurabh already touched on, which is I'm going to try to be careful about separating out the explosion mechanism from what the companion is doing, what the progenitor system is. And I think it can be a little confusing because sometimes people conflate the two. So we'll talk about single degenerate systems when really what we're talking about are single degenerate change or sacral mass explosions. Right, and the same with double degenerate scenarios. Often people actually mean double degenerate change or sacral mass scenarios. But there's this whole class of other explosion mechanisms, this double detonation, which I'll go into more detail about, that encompasses both single degenerate and double degenerate scenarios. So you can have single degenerate double detonations and double degenerate double detonations. But in the first half of the talk, I'll be talking in general about double detonations, regardless of how they're triggered, whether or not the progenitor is another non-degenerate star or another degenerate star. Okay, so for the first half of the talk, I'll talk about double detonations in general. In the second half, I'll focus more on a specific subset of double detonations. So just to make sure we're all on the same page, here's a movie showing what a double detonation looks like. So what we're seeing here is a cutaway through a white dwarf. Here's the North Pole, here's the South Pole, the equator is over here, and the center is here. This white dwarf, it's a carbon oxygen white dwarf and has a helium shell on top. And so we're going to trigger a helium shell detonation at the North Pole. And it's going to sweep around past the equator towards the South Pole. Oh, sorry, I should mention what we're looking at. The colors are temperature, so hot is red and blue is cold. And the contours are isodensity contours. Okay. So here goes the helium shell detonation. It's sweeping around towards the equator. And as it goes in, as it laterally propagates, it sends in a shock wave, which you can see by the perturbation in the isodensity contours. And that shock wave eventually converges near a point and forms a carbon core detonation. Okay, so that's why we call it the double detonation scenario. This is slightly different, I should mention. This is slightly different from the movie Fritz showed, because in that scenario, they actually trigger the carbon detonation down here. But it's sort of similar. Basically, you get a helium shell detonation in the northern hemisphere, or what I'll call the northern hemisphere, and a carbon detonation in the southern hemisphere. Okay. Now, the double detonation scenario in general has a pretty rich history. It started almost as early as the change or sacral mass scenario. So it started in 1980. Double detonations then, at that time, took place in pretty thick helium shells. And so the helium shells were something like 0.1 solar masses. And as a result, the helium shell ashes left a lot of sort of undesirable effects on the type 1a light curves. In more recent years, we've been focused on helium shells that are much thinner, something like 1/100th of a solar mass, or even less. And that is the result of a different progenitor scenario. So if you have another white dwarf donor, then that leads to much smaller helium shells at the time of explosion. And as a result, we might hope that that leads to less observable effect in the type 1a supernova spectra. Now, I wanted to talk about some of the recent progress we've made in the past year doing radiative transfer on these subchange or sacral mass explosions. The first point I wanted to touch on is the importance of non-local thermodynamic equilibrium calculations. So to remind you from your grad school radiative transfer classes, LTE, local thermodynamic equilibrium, is the assumption that all the level populations and the ionization states of the atoms in your supernova ejecta are given by Saha-Boltzmann. So that's, you specify a temperature, and that tells you the ratios of the level populations, and you can calculate your opacity and calculate your radiative transfer. So it's relatively easy. You just specify a temperature and you know the states of all your atoms. But unfortunately, real life is not that simple. And so we have to go to non-LTE to get a little more exact. In non-LTE, we don't make that assumption. Instead, what we're doing is calculating all of the radiative transition rates and all the collisional transition rates between all the level populations, and then setting that into equilibrium and then calculating the opacity that way. It's a lot more computationally intensive, but it can be necessary, especially in the photosphere of a supernova ejecta, where the ejecta is starting to become optically thin, so you're not able to maintain a Saha-Boltzmann distribution. So here, what I'm doing is showing the LTE and non-LTE calculations for 3 different times for a subtrainer sacral mass explosion. So this is a 1 solar mass explosion. 0 days, so this is next to B-band maximum, 15 days from max, and 30 days from max. Now at B-band maximum, the LTE approximation isn't so bad. If you look in detail, there are some differences between these LTE and non-LTE spectra, but overall it's a pretty good approximation at maximum light. But as soon as you go past maximum light, at least for a subtrainer sacral mass explosion, non-LTE effects are really important. So it's very obvious in the U band and the B band, between 4,000 and 5,000 angstroms, you see a lot less absorption in the non-LTE spectrum. And that's as a result of there being less iron in the singly ionized state, which is where you get all this iron line blanketing in the LTE spectrum. Okay, so when you go to non-LTE, you expect the U band and the B band to be brighter 15 days after explosion. 15 days is obviously a very useful, important time if you care about the Phillips relation, or in general, if you care about the shape of your light curves. So I'm showing here is after you do those non-LTE calculations, what does the Phillips relation look like? Just to remind you, the Phillips relation is the peak magnitude in B band versus the decline rate in B band. So how much the light curve drops 15 days after maximum. The gray points are observations, and the colored points are our non-LTE one-dimensional explosion models. What we see is that the color points do indeed follow the Phillips relation. This is great. So this is a really exciting result to see. The subluminous explosions match the subluminous, sorry, the 0.85 solar mass explosions match the subluminous type 1A. You get a normal 2011 FE for a 1 solar mass explosion, and 1.1 gets you some overluminous 99 DQ or 99A type explosion. The different points are 2 different radio transfer codes in non-LTE. So one is Sedona, one is CMF-Gen. They're quite different codes, but the fact that they give results that are pretty close to each other gives us some confidence that we're doing this correctly. The different shapes of the points are different carbon oxygen mass fractions, so it does give some variance depending on what you assume for the initial mass fraction. But overall, what we see is a pretty good reproduction of the Phillips relation. Now, I should mention that non-LTE is crucial for this because when we did this in LTE a few years ago, with exact same explosion models but different rate of transfer, we got pretty different results. So for the subluminous 0.85 solar mass explosion, it was pretty similar. But by the time we got to a 1.1 solar mass explosion, it had a delta M15 that was closer to 1.5. So it was like here. Just going to non-LTE, well, quote unquote just, I mean, it took a lot of effort, but going to non-LTE moves this point over almost a full magnitude in delta M15. So it's crucial if you care about your rate of transfer observables after maximum light, it's crucial that you use non-LTE. If you can't do non-LTE, then you just can't make predictions past maximum light. So that is what we're able to do in 1D. It's because it's a relatively simple explosion model. There aren't that many points. However, going to multi-D, which is obviously necessary for an asymmetric double detonation, right now, currently, we can't do non-LTE in multi-D. It's just too expensive. Okay, but however, we can hopefully still get some useful information out of multi-D explosions, and hopefully in the future, we'll push to non-LTE and multi-D. Okay, but for now, we are confined to doing LTE calculations in multi-D. What I'm showing here are explosion models from a suite of calculations done by Sam Boose, who's a grad student at the University of Alabama working with Dean Townsley, my collaborators on this. And this is to give you a sense of what explosion models look like in multi-D. Okay, so these are mass fractions of silicon, calcium, and nickel in velocity space after they've reached homologous expansion. In all these simulations and what I'll show in the future, again, I'm assuming that the helium shell detonation is initiated in the northern hemisphere and the carbon core detonation gets triggered in the southern hemisphere. So that's how I'm going to define my coordinates. We can see that there's definitely some asymmetry imparted by the asymmetric explosion. In particular, we see more silicon and calcium. It extends to higher velocities in the northern hemisphere than it does in the southern hemisphere. Right, so the intermediate mass elements go all the way almost to 20,000 kilometers a second in the northern hemisphere, but they're confined to roughly 10,000 kilometers per second in the southern hemisphere. And this will obviously have effects on the, it will give viewing angle effects, like Fritz mentioned, on the light curves and spectra that we look at, that we see. So here I'm showing light curves. This is bolometric U, B, V, R, and I light curves for a subset of our models. The red lines are for 0.85 solar mass explosion, and the 1 solar mass explosion is in blue. And the different line styles are different viewing angles. So when looked at from the north, that's the dashed line. The equator, equatorial viewing angle is the solid line. The dotted lines are from the south. there's definitely some viewing angle dependence. So looking from the north first, the dashed line, it's dimmer. And as you move to the equator in the southern hemisphere, it gets brighter. Okay, it's much more pronounced in the 0.85 solar mass explosions. And this is a consequence, again, of the different density distributions. The light takes different amounts of time and more of it gets absorbed on its way out and adiabatically expanded on its way out in different hemispheres. Okay, so that's why we get a viewing angle effect. There's even more of an effect in the spectra. Okay, so this is a, for one given model, this is a 1 solar mass explosion looked at from 3 different viewing angles, again, from the north, equator, and south, all compared to the same spectrum, max light spectrum of 2011 FE. So looked at from the north, there's not a great agreement, okay? Not only are the absorption features different strengths, but also the velocities are different velocities, okay? And that's a consequence, again, if you remember the explosion model plot I showed before, the intermediate mass elements extend to higher velocities in the northern hemisphere. In the southern hemisphere, the agreement is better. It's not perfect, but it's much better than it is from the north. But from the equator, things I think are looking pretty good. We get a lot of these velocities and absorption features correct. I think the biggest discrepancy is here. So this is a silicon feature, 4130, I believe. What we have seen though in our non-LTE, our 1D non-LTE calculations is that the strength of this feature can definitely change when you go to non-LTE. It does go in the right direction. So we're hopeful that this will be fixed if we are able to go to non-LTE. Okay, and a lot of these other features match nicely as well. So this is from one particular spectrum, one particular model. We have a whole suite of models and a whole bunch of viewing angles. And so we can look at how these things correlate with observations at maximum light. And again, I should emphasize, these are all LTE calculations. And so we can't go past maximum light, at least not in a trustworthy sense. So I'm showing here are different correlations between maximum light observables. Looking at color, so this is B minus V at B max minus V max, the peak B band magnitude, and the silicon velocity, that main silicon line, the 6355 at B band max. Okay, so let's look at one panel first. So this is looking at how bright the supernova gets versus some proxy for its velocity. The gray points are observables, gray points are observations. Okay, we see that they form this sort of triangle that fills out the parameter space, but sort of avoids dim, dim supernovae with high silicon velocities. The colored points are theoretical models, observables from our theoretical models, ranging from a 0.85 solar mass explosion to 0.9, 1, and 1.1. And the different darkness to lightness is the different viewing angle. Okay, so the lightest points are looking at from the south, where the carbon core detonation is initiated. The darker points are from the north, where the helium shell detonation is initiated. So to 0th order, I think we're doing pretty well, right? We sort of mark out this space and we avoid this region where we don't observe supernovae. Okay, so to 0th order, I think we do quite well. Looking at a little more detail, there are definitely some discrepancies. So for example, this 0.85 solar mass explosion, these different viewing angles, they extend to lower velocities than are observed, and they extend to dimmer supernovae than are observed, right? And I think what this is telling us is that the minimum mass for a white dwarf that can explode as a type 1a supernova is just between 0.85 and 0.9. So it's like a 0.86 or 0.87 maybe. Below that, the densities aren't high enough to propagate a detonation. So maybe the minimum mass should be more like 0.87. And that would get us the right range here. At the high mass end, everything's doing fine until we go to the northernmost viewing angles. And there we start to get velocities that are really high, extending all the way out to 18 or 19,000 kilometers a second, which are not observed. I think part of this has to do with the the LTE approximations that we're making. So when we did this in non-LTE in 1D, what we found is that for the highest mass explosions, we didn't get as high velocities as we did in LTE. So there will definitely be some correction if we're able to go to non-LTE, which will move these over. Hopefully they'll move them all the way over here. Maybe not all the way over, maybe they'll be extending maybe something like this, but that could also be a function of selection of a sample size. Okay. When we look at color, there's definitely more of a discrepancy. So if we look at this panel here, this is looking at color versus the peak magnitude in B band. The observations show a pretty nice correlation. Oops, should have clicked that. Nice correlation between these two quantities, right? So the brighter things are relatively bluer and the fainter things are relatively redder. Our models extend to are just generally redder, okay, especially in looking at it from the northernmost angles. This is also, I think, a non-LTE LTE effect. I should have mentioned, sorry, that these error bars are showing the differences between LTE and non-LTE calculations from our 1D models. So to give a sense of what the changes could be if we're able to do multi-D non-LTE. What we saw in our 1D calculations is that the brighter explosions were bluer after the non-LTE corrections were put in. Okay, so these will move over to the left. How much they move over, it's not quite clear. I mean, we can't draw a direct parallel between 1D and multi-D calculations. But if they move over enough, that should bring them in line to what we see in these observations. Again, with the 0.85 solar mass calculations, these are just really, really red. Just really, really red, like way too red. There's no way that non-LTE corrections are going to help us here. And again, I think this is what this is telling us is that 0.85 solar mass explosions are too low in mass. They don't actually explode in nature. The limiting mass is more like 0.87. Okay. And this plot is just the other, this is color versus silicon velocity. We see similar conclusions that from the other panels. Okay, so those were the recent progress we've made in our general double detonation calculations. What I want to spend the last few minutes talking about is a subset of double detonation calculations where the companion is another white dwarf and it's starting to merge unstably with the white dwarf that eventually explodes. And this is what we started terming the D6 scenario. So that's dynamically driven because they're driven by a merger. Double detonations, they're double detonations and double degenerate because it's another white dwarf as a companion. There are a lot of interesting things about this scenario that makes us favor it. But one of the more important things is the question of what happens to the companion. So in this really nice simulation done by Rudiger Packmore, sorry, I should explain it. What we see is the density, the temperature, and the mean atomic weight. This is a companion white dwarf that's starting to be tidally disrupted by the more massive white dwarf. Material is being pulled off very rapidly, and it results in a high density and temperature where that accretion stream impacts the white dwarf. And eventually that density and temperature gets high enough to trigger a helium shell detonation. So it's the merger itself that triggers the helium shell detonation, and that then triggers the carbon core detonation. Okay. The interesting question is what happens to this companion? That's because, sometimes when you think of a merger, you think of a complete disruption of a star and the formation of a single merger remnant. However, what we mean by merger is just the beginning of the merger. It's possible that the explosion of the more massive white dwarf can happen before the companion is fully tidally disrupted. And if that were to happen, then we predict the existence of a surviving white dwarf donor. This is the companion that was not fully tidally disrupted before the explosion happened. If that is the case, there's a really unique signature for this model, which is the existence of a hypervelocity surviving donor. So Saurabh already touched on this. What I'm showing here is the orbital velocity of a companion at the moment of Roche lobe overflow for different progenitor scenarios versus the mass of that companion. So main sequence stars, non-degenerate stars in general, they can get up to fairly high velocities if they're low in mass. But it's not until you get to a white dwarf that you get above 1,000 kilometers per second. So if you have a white dwarf companion, you can reach orbital velocities that are between 1,000 and 2,500 kilometers per second. If these were to survive, it's a very unique and pretty obvious signature of this scenario. Now, normally in astronomy, we have difficulty finding distances, and thus we have difficulty deriving actual velocities. But with Gaia DR2 and Gaia EDR3, we were able to do so to a pretty large volume. And what we were able to find was 3 stars that had the right velocities to be the surviving companions of D6 type 1a supernovae, which we've helpfully labeled D6, 1, 2, and 3. As you can see, these are posterior probability distributions of the total velocities in the galactocentric reference frame. The 3 velocities are exactly in the range we expect to see, between 1,000 and 2,500 kilometers per second. Okay. So that was a very, these are just the 3, by far the 3 fastest stars that were detectable by Gaia. When we put them in the CMD, they occupy this interesting space. They form a class here, and they occupy this interesting space between the white dwarf cooling track and the main sequence. And so what we think happened, obviously they're not white dwarfs now. What we think happened is that they were white dwarfs, but they were beginning to be tidally disrupted. So some of the orbital energy of the orbit was being put into them. In addition, when the supernova happened, the impact was also able to inject some energy. So that is why their radii are so inflated now. They're on their way to cooling back to becoming white dwarfs. But they're currently radially extended and thus bright enough for us to have detected with Gaia. We were able to get spectra of these stars, and what we saw was also very interesting. The stars are very similar to each other, but also very different from any other star. Many, many strong features of carbon and oxygen, as well as magnesium, calcium, and we're currently going through the high resolution spectra, but lots of iron group elements as well. This is exactly what we expect to see for a carbon oxygen white dwarf that got a lot of thermonuclear ash from a type 1a supernova dumped onto it. And the final piece that really cements these things as being a class of surviving stars that came from type 1a supernovae is the identification of one of the stars with a known supernova remnant. So this remnant is the furthest from the galactic plane, which is pretty indicative that's an old stellar population, likely a type 1a supernova. The estimated age of this remnant matches the travel time of this star from this point. So, and the distance is also consistent. So we're pretty confident in this identification of this star with a known, likely type 1a supernova remnant. And it also happens to be the only one of those stars that has a high resolution HL alpha map to search for a remnant. So it's possible that the other two stars are also, they also have supernova remnants associated with them. We just haven't found them yet. Okay, so I'm going to start wrapping up. In the first half of the talk, I talked about our recent progress on radio transfer simulations of double detonation supernovae. They had, we had discussed them in the 80s. They fell out of favor, but I think I can confidently say they're back now. And the reasons are that we have larger nuclear networks, which allow much thinner helium shells. In non-LTE, which we've been able to do in 1D, we're able to reproduce a lot of nice things, including the Phillips relation. And in 2D, although we can only do LTE calculations, we can still look at maximum light observables, and those match a lot of the correlations we see. There are discrepancies, but hopefully when we're able to push to non-LTE in multi-D, that will fix these differences. In the second half of the talk, I mentioned that we've discovered what I think are the best known cases for surviving companions of type 1a supernovae in the form of these hypervelocity D6 survivors. They have the right velocities and the compositions, and one comes from a remnant. The current questions that I'm really interested in are where are the other D6 survivors? So I've mentioned we found 3, but in that same volume, there should be something like 300 or 400. Okay, so we found 1% of them. Is it the case that that's all there is? It's just 1%, and only 1% of 1As come from this scenario? I don't think that's the case. What I think is happening instead is that these are just the 1% that are the brightest, and thus we were able to see them. The cooling time scales are such that they dim below the detection limit of Gaia. So I think there are another 300 or 400 in the solar neighborhood that are moving at thousands of kilometers a second. The only question is, how are we able to get distances to them and actually see that their proper motions convert to high velocities? Is there a way we can take spectra in a systematic way and identify them that way? And with that, I will end. Hopefully we will be able to find these other D6 survivors in the coming years. Thanks.
Thank you very much, Ken. We'll run a little bit with questions. I was really very much excited about these double detonation models, the new ones. But I remember that there was a problem with the early double detonation at late times, that I guess you may face part of this problem with the late time spectra, that they have too little collisional excitation of some lines that are really needed. Like for instance, for 2011 FE, that has been very well explained by Chandrasekhar models. Don't you? I think that you are working on this, no? But
what do you mean by late time? Do you mean nebular spectra?
Nebular, yes.
So I've done no work on nebular spectra, but I think Abby's going to talk about sub-Chandrasekhar mass nebular spectra. So maybe she'll have more to say in her talk.
Okay.
Yeah, I've only done 1D nebular, but we can talk about that a little this afternoon.
Mm-hmm.
So I've seen Fritz, Mario, and Wolfgang's hands go up, I think in that order.
Right, Ken, thanks for the nice talk. I have a question about the 2D or multi-D simulations that you showed with the double detonation scenario. If you go back to that slide, so my question was, actually, you seem to have, here, you seem to have quite a bit of small scale structure in these in the composition of the ejector. So why is that? I mean, it's detonations in the end, right? And it should be rather smooth. And there are these bumps in there, and yes,
This
and
kind of
also
material here?
also in the inner part, right?
Yeah, so I think that's what's it, Richter Meshkov, is that right? So you have this. So the first part is the helium shell detonation, and it's being pushed into some fluff that we have in the simulation.
Right.
This is yeah. So we're showing mass fractions, but the actual density is quite low here. So I'm not too worried about that. Here, this is the core detonation pushing into the helium shell detonation, so reaccelerating it. So I think that's a result of essentially Rayleigh-Taylor from the secondary acceleration from the shock. So I think that's right. I mean, these are 2D simulations, so the actual extent of these fingers are probably not, correct, because the turbulent spectrum is not entirely right, but that's the basic idea behind this.
Thanks.
Perhaps we can go to Mario.
Yeah, good morning from this side of the world. Thank you very much, Ken, for this beautiful talk and fantastic models. I wonder if you have compared your models with spectropolarimetric data of type 1a supernovae.
We have not. The radiative transfer code does have that capability. I just haven't turned it on and explored that yet. So yeah, we do expect some amount of polarization because there is some asymmetry. And the question is, how much is there? Does it still match the pretty low polarization seen in 1As? So that's a good question. We'll be looking into that.
Thank you.
Wolfgang?
Thanks, Ken, for the really nice talk. And just an update, so we have DEChem imagery of 1006, and so led by Josh Shields, who's one of my students. And so we'll, as soon as we have some better astrometric measurements, we went really deep, I think 2 or 3 magnitudes deeper than the D6 stars. And so as soon as we get the astrometry under control, which is harder than it seems, we'll let you know, and would love to have your opinion. The main thing that I wanted to ask is I really love the NLT models, and I'm also really happy that you're saying essentially everything before maximum light we're safe with, not full NLT, but when we use nebula approximation.
So, sorry, just to be clear though, the bulk things like the light curves are probably pretty good through max. Specific spectral details, so like line depths and things like that, might not be quite as robust.
Okay, so you're saying even at -10 days?
-10, yeah. So we didn't look at -10. I don't know about that,
okay,
but at maximum.
Okay, so I mean, we also don't. You use normal full Saha-Boltzmann. You don't use these nebula ionization approximations or dilute LTE, where you sort of dilute.
No, it's just regular Saha-Boltzmann with LTE. Yeah.
Okay. And so the main question, as we're sort of also moving in that regime, is that scares the shit out of me is the atomic physics. How well do we know, sorry?
You're being recorded,
Oh yeah, sorry. Is this a PG-13 conference? Which scares me is the atomic data. And I'm wondering, I mean, when you sort of put the atomic data together, are there many sources? I mean, how stretchable is this? Is there a factor of 2 in there, or are we closer?
Yeah. So the only test that I did was so the data I'm using is from the CMF Gen site. The only test I did was different amounts of lines from that data set. So we are converged in using that data set as a baseline. We're converged in the number of lines we're using from that data set. But if atomic data were to change and that data set is wrong in some lines, then we wouldn't see that. We wouldn't be able to recover that. So I can't speak to that uncertainty.
Okay. Well, thanks a lot, Ken, and very nice talk.
Okay, thank you very much to everyone, all the speakers for the first section before the coffee break. Now I think we have to adjust the time for the coffee break because we are late. I would suggest to have 2 minutes as coffee break, and then The next speaker will be Xing and Bob. You want to lead the discussion and take cover from me?
Sure, absolutely.
Okay.
We'll reconvene in 2 minutes. Xing-Chi, are you there? Hi, Xing-Chi, would you like to get your slides up? Okay, excellent. So, and what I'd like to suggest is just in order to preserve the time for the roundtable discussion, I'll just perhaps give you a sort of like a 5-minute indication. So after about 15 minutes, and that would still give us about 5 minutes for questions and answers. But you know, potentially could whittle down to around 3 minutes or so. That way, we'll try to keep everyone keep as close as possible to the original schedule. So with that, really looking forward to our talk. Xing-Chi, take it away.
Good morning, everyone. So thank you, Peter and Robert, for inviting me to this give me this chance for the overview talk. So I'm Xing-Chi, a second-year postdoc of Caltech. So I will tell you about how the chemical compositions reveal the stories about Taiwanese supernova explosion. Is it moving? No. Yes. So the observational data of Taiwanese supernova has given us a lot of insights that the supernova is universal only for a small subset. So to explain the many diversified explosion patterns in the catalog, in the literature, there are a number of models already proposed as I list here, and we can classify them according to their pre-explosion mass, namely the transitional mass model and the subtransitional mass model. So many of the well-known models are listed here, for example, the DDT model or the double detonation model. In observations, Taiwanese supernova is tied to an outstanding question whether Taiwanese supernova develops from the single degenerate or double degenerate scenario. So just for the review purpose, I just briefly mentioned the single degenerate scenario means the companion star being a main sequence star, red giant, or a helium star. While for double degenerate scenario, it means the star is a white dwarf. But I have to make a remark here that when I argued whether the supernova explosion being a transit mass model, it is not equivalent of arguing whether we are supporting the single degenerate or double degenerate scenario. So to illustrate the idea, so I show the diagram here, which shows the evolution of the white dwarf accreting mass from a hydrogen-rich envelope. That is the single degenerate scenario here. And you can see the final evolution depends strongly on the mass accretion rate, as well as the initial mass of the white dwarf. And depending on this parameter, the white dwarf can explode in either transit mass and subtransit mass. So therefore, we are only talking about whether the model being more preferable for transit mass or subtransit mass rather than being single degenerate or double degenerate. So in this talk, I will try to look at different systems to see which model, transit mass or subtransit mass, are more favored to explain the observational data. So thanks to Fritz and Ken, who have already given a very detailed overview on a lot of topics, so I can save some time in the introduction part. So I will just briefly go through about the introductory physics here. So we know that the Taiwanese supernova is the explosion of carbon-oxygen white dwarf because of the nuclear fusion along the alpha chain, and the light curve receives the radioactive decays of nickel-56 and cobalt-56. But there are subtle differences which I should mention here at the beginning that so I list a lot of important features here, and I mark those in the red color. So the first important difference is that the transit mass model has a much higher density. So you can see this is about 10 to the 9 grams per cc, but for subtransit mass model, it is 1 to 2 orders of magnitude lower. At the same time, we can also see that the flame, the transit mass model has the explosion supported by part by the subsonic flame, while that in subtransit mass model, it is supported by the detonation. Why the notation of flame appear in the transit mass model can be understood by this figure, which shows the relative change of pressure before and after runaway as a function of density. So here are the density in the subtransit mass regime, and here is the density for the transit mass model. And the number here corresponds to the white dwarf mass. And we want, there are a number of lines here, and we only want to focus on this line. We can see that the pressure jump of the matter decrease when the density increase. So this is because when the density increase, the matter become degenerate and the electron degenerate pressure start to override the thermal pressure. And therefore, in a high density environment, it is less likely for the nuclear runaway to trigger shock. And also because of that, the nuclear runaway appear in a subsonic flame rather than a detonation. So, but a white dwarf with only subsonic flame cannot explode successfully because the flame is too slow to burn everything. So we always need some transition into detonation, and therefore this is the well-known deflagration detonation transition. So here I just show you our own version of simulation for the transit mass model using the DDT mechanism. We can see that indeed the flame, which burns from the center to this size, about 1,000 kilometers, take a very long time, about 1 second to do so. And then after the DDT start, the DDT can burn almost everything within a very short time. You can see from this time slot to this time slot is only about 0.1 seconds, almost 10 times faster. And this process allows a large production of energy, and therefore the white dwarf can successfully explode. On the other hand, the subtropic mass white dwarf is stable to exist alone. So we always need some trigger, such as the accretion from the companion star or by the Rowland merger. And through either of the process, it creates a runaway in the helium envelope where the helium detonation develops like this way. And the helium detonation later create a shock in the carbon-oxygen core, which triggers the carbon detonation. And this carbon detonation burns everything and creates an explosion. So both mechanisms have actually a very solid picture in how the white dwarf explode, and both of them can generate models to explain the Phillips relation, including both the transit mass model and the subtransit mass model. But there are both pros and cons in both pictures. For example, for the transit mass model, it can produce a significant amount of manganese and neutron-rich isotopes, but there are discussion or worry about how robust the DDT is. And the manganese is important for Taiwan supernova because this is, so far as I understand, the only source which we can make most of the manganese in the universe. On the other hand, for the subtransit model, it has more optical evidence, but it has an issue about making how much manganese and nickel and how robust the carbon detonation trigger is. So to examine the two models, we usually do the tracer particles to examine the chemical signatures. So what we do is to use the tracer to record the density and temperature evolution as a function of time. And because the trajectory of Taiwan supernova is rather simple, so we can characterize the trajectory by its peak temperature and peak density. And by these two parameters, we can tell roughly what is the final chemical abundances is in each tracer. So in the low density regime, we have those incomplete burning where we have those magnesium, silicon, calcium. And then in the high temperature, low density regime, we have the alpha rich free cell. And in the high temperature, high density regime, we have the nuclear statistical equilibrium, NSE, where we can find those odd number elements and neutron-rich isotopes. So to illustrate how to apply this tracer particle to the nuclear synthesis, I do a numerical experiment here. So we try to assume the tracer to start with some peak density and peak temperature here, and then we let the tracer to expand. And the expansion time scale is chosen according to some typical explosion energy, let's say 10 to 51 erg. And then we use the full nuclear network to calculate the final chemical abundances. And then here we show a lot of details here, but I would like to draw your attention to this part, the final electron fraction. The line here corresponds to the free regime I just mentioned in the previous slide. We can see that most of the electron capture can only take place in this regime, which is in the transit mass regime in the NSE. And this is also the regime where you can find most of the manganese being produced. So this is some of the important features which we will apply to the later application of supernova nuclear synthesis in explaining real observational data. So here are the tracer particle in some real supernova models. So the left one is the tracer from the transit mass white dwarf, and the right one is from the subtransit mass white dwarf. We can see that in the subtransit mass white dwarf, we have a very thin line of tracer here. So these are the tracer being burned by deflagration, and they are those which make most of the manganese we can find. On the other hand, the density for the tracer in the subtransit model is generally much lower. And therefore, you can find that the production is really low in the manganese abundances. And then we can apply this tracer to calculate the full nuclear synthesis pattern to know how the chemical abundances is. So this is the mass fraction of the two models, the transit mass and the subtransit mass model here. The notation here is the standard one, which is the mass fraction of that isotope scale with solar value and taking the log scale. So I also add two lines here so that to characterize which part is overproduction, which part is underproduction. And of course, we want to focus on the mechanism, and you can see here the mechanism for the transit mass is quite close to the solar value. On the other hand, for the subtrandra model, the mechanism is slightly underproduced. It is because of the density and those NSE effects I mentioned in previous slide. And these kind of features can be very useful for connecting real data with numerical models. So now we will move on to examine different astrophysical systems and see how the chemical signature tells us the real story of supernovae. The first example is the supernova remnant Sagittarius A. So my collaborator Ping Zhou has measured the spectra of this beautiful supernova remnant. And then she derived the chemical abundances shown by the data point here. And then we try to compare models of different classes with this set of data. We can see that this is the subtrandra sigma mass model. We can see that because of these upper limit here, the subtrandra model tends to overproduce the intermediate mass element, that is the sulfur, argon, and calcium of this object. Meanwhile, the nickel 58 is too small. On the other hand, we can also look at the transit sigma mass model. On the left-hand side, we have the model with DDT. We can see that the sulfur, argon, and calcium are still overproduced in some extent. And also the manganese and nickel over iron ratio is also slightly off. And given this is a very precise measurement, so we think this is not the complete solution to the observation. So we also examine the version without DDT. That is the typical Type 1ax supernova. And we can see that most of the data point can fit much better now. So this is an exciting news for us because the Sagittarius A, which is the supernova remnant in our galaxy plane, is the first Type 1ax remnant observed. So I hope this example illustrates how we can use the chemical elements to distinguish the explosion mechanism. And then we can also use the chemical abundances to distinguish the explosion progenitor. In the follow-up X-ray observation by UK and Oshiro in JAXA or in the University of Tokyo, so he measured the spatial distribution of the iron group element in this supernova remnant 3C397. And this object has been observed by his collaborator Hiroya Yamaguchi. So he finds that the high manganese over nickel ratio is a feature pointing to the transit sigma mass model explosion. So in this work, we try to push further to see which model in the transit sigma mass regime can explain these kind of features. And they have observed the chromium over iron ratio here, marked by this line and this line. Basically, they are the same plot, but for different tracers from my models. So we try to compare different models in the transit sigma mass regime. We find that for the low mass model, so the model is about 10 to the 9 gram per cc, so 1.33 solar mass, all the tracer cannot reach the high value observed. So this means that the low mass transit sigma mass white dwarf is less likely to be the origin of this supernova remnant. On the other hand, we can see a large bunch of tracers can reach this high value of the chromium over iron ratio. So this is a good sign that the supernova remnant 3C397 is not only the explosion of a transit sigma mass white dwarf, but the explosion of a high mass transit sigma mass white dwarf. And the second last application I want to show is the galactic chemical evolution. It is because I want to show that because even I have some supernova remnant being shown to be an explosion of transit sigma mass white dwarf, it does not tell us the whole story. So we need to look at some larger system to see how each of the model contribute to the universe. So this work is done with Chiaki Kobayashi. So using her galactic chemical evolution code with my supernova nuclear synthesis result, we can show that we can show different lines here. So here are two sets of lines. So this line assumes that
15 minutes.
Assumes that all of the supernova explode by pure transit sigma mass white dwarf, and these are those purely contributed by pure subtransitional mass white dwarf. So you can see that in order to reproduce not only the trend, but also the magnitude of the data, we need to have something like almost close to pure transitional mass white dwarf to reproduce the observational data. But of course, the exact interpretation depends on different galaxies, because each galaxy has its own formation history. So if we want to even look at a more general solution, we need to look at larger systems such as the galactic cluster. So this is the result obtained by another observer, Aurora Simonescu. So she had the Hitomi result for this Perseus cluster. You can see that this observation is extremely high precision. The error bar is much lower than those taken from previous generation telescope, Suzaku. And if we want to fit this set of data, given the very tight limit here, we find that the best fit model will be assuming pure transitional mass white dwarf. But of course, this is not a good approximation from the first place. So if we consider the transitional mass white dwarf fraction as a model parameter, so just like this line here, so which takes the model taken from Ken Shan's models, the D6 model. So we still need about 30 to 40% of the Type 1a supernova population being transitional mass white dwarf. So here's the end of my talk. I think I already run out of time, I guess. So I just leave the current story here, and I will just make a short work about Chrism that it will, because this is the descendant of the Hitomi. So we expect that it will continue to give us a lot of interesting spectra and very precise spectra, which will challenge our understanding and give us also a challenge in the modeling. Thank you for your attention of my talk.
Thank you, Xinqi. That was an excellent talk. We have time for some questions. Wolfgang?
Hi, thanks, Xinqi, for this really, really nice talk. So I'm wondering about 3C397. So you mentioned this is the first 1AX remnant. And so I was wondering if this is, you're inferring this from the high manganese abundance, or is there other measurements?
No, this one is we do not infer it to be the 1AX. We just infer to be high mass transitional mass model.
And sorry, then I guess I got my remnants mixed up. The one before, you mentioned this one. Yeah, exactly. First 1AX remnant. So how do you know that this is a 1AX remnant?
Basically by these two patterns. So we think that so if it is Type 1a, then the how to say, the interpretation is not perfect. I mean, at least it is not better than this one. So the Type 1x model seems to fit better than the Type 1a model.
So it's consistent with the 1ax, but I guess that doesn't mean it's necessarily a 1ax. You're just saying
right.
It's consistent with.
Right.
Thank you.
Fritz?
Yes, thanks for the talk, Xinqi. I was wondering, your double detonation models that you showed, do they actually produce, what's the manganese over iron ratio they produce? I mean, you have shown the tracer distributions there for your subtransitional mass explosion models, and they didn't seem to produce manganese a lot, right? But we actually find that in the helium shell detonation, you do produce manganese, right? This one here.
Yes, actually, it still produces. So you can see it is still close to the solar value, but so this is the region where we can find some of the, maybe the color is quite pale to see, but this is the region where the manganese can be produced.
Yeah, but that's the core detonation, right? So where is actually the helium shell detonation there?
Pardon?
But that's probably the core detonation that you were showing there. So where's the helium shell detonation?
You mean which tracer are coming from the helium detonation?
Yes.
I think it is also around here too, but I forgot to classify it. So,
yeah, usually you see very different tracks, and then you actually see in the helium shell detonation a very pronounced production side of manganese as well.
There is a band at a temperature of 2 × 10⁹.
Yeah, there's something very faint down there. Yes, maybe that's it. Yes. Okay, anyway.
Okay. Thank you, Xinqi. Let's move to Wolfgang.
So I'm going to keep myself honest, Bob and Pilar. I'm going to put 15 minutes on the timer. When it goes off, it's going to be ding, 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 ding.
You can
Anyway.
take a couple extra minutes. We have 20.
Well, I mean, no, but then the thing has already shifted, so I'm trying to help out. We'll see how successful I am. Can everyone see me and hear me? Let me just.
Looks good.
Somehow this is. There we go. Sorry, I need to rearrange my screen. I'll be there in a second. Well, thank you very much for the invitation to this breakout session. And I think this is so nice that like Pilar and Bob are organizing this. I think we have a drought of 1A meetings. And I think this is really a pleasure to sort of be able to connect to the community, even though it's unfortunately only virtual, and hopefully this will change very soon. I know that these are crazy times and people are at home. And so I also want to acknowledge that if you need to leave for any reasons, like dealing with kids or loved ones, so please do. I fully understand this. First of all, I want to also thank Saurabh for pushing us in the direction of saying these are not necessarily only 1As, but I mean we're trying to figure out why white dwarfs and canary. Oh, I need to actually put my timer on. Why white dwarfs explode and canary said I'm not allowed to use swear words. And so one of the things I think that is quite cool is we can do insights from spectral time series. So this has been done before, but I think we're getting to the point where we can do this really in a probabilistic sense. And I'm going to get into this a little bit further. But first, let's talk a little bit about an introduction. The main question that we're all asking is why TF white dwarfs ignite? So that is really, I think, the main question. They just shouldn't, and I think that is the main puzzle that is there. And so while Fritz has given a much better explanation than I will, I think I can be better than Fritz's talks in the key aspect of keynote effects, and can say the reason or the main conditions for white dwarfs sort of exploding is crossing this line from neutrino cooling, where neutrino cooling sort of dominates, to the regime where carbon burning will sort of dominate. And so the main question about 1A supernovae, as far as I can tell, is exactly where and how do we cross this line? And so the main discriminant that I want to jump on today is that the burning from the flame propagation does not only lead to different nucleosynthesis, but also sort of mixes through material. So essentially what we will get in the end is we have, for the different progenitor scenarios, for the near Chandrasekhar mass slow accretion scenario, and for the double detonation with the many extra Ds that Ken Shen added, and the merger scenario, we sort of do this at different spots in this curve. And so there's many discriminants we can sort of go here for, but I think one of the discriminants is that one of them is a detonation, and the other one is a deflagration to sort of detonation transition, as has been mentioned multiple times here in this talk, and the last one, Xinqi. And so what we could potentially do is, if we had a technique to reverse engineer the explosion from spectral time series, we could sort of tell the difference, right? And so this is what I'm going to talk about. And this is a technique called supernova tomography, and this is not a new technique. I mean, I know many people have done this, groups around Matsali et al, and I'm going to specifically mention the Steele et al. 2005 paper have sort of done this. So how does this work? What do we do? So this is 4 days after explosion, the white dwarf is sort of expanding, and I'm indicating here with the red a photosphere. I mean, people will yell at me and say, well, Wolfgang, there's not really a photosphere, but I mean, I think there is sort of a surface overlap scattering that works for many wavelengths, and I think it's a sort of useful approximation. And as we go on in time, this surface overlap scattering essentially goes further into the white dwarf, and we see layers, more and more layers being exposed, and essentially we see an imprint on this. So as we can see, like, this is expanding, and while this is happening, both of them are expanding, but we see more and more layers being exposed. And so we can think about this, that this is amidst a smooth continuum, right? A thermal continuum as an approximation. And then the features imprinted on top are sort of the elements synthesized in the explosion. And so in theory, what we could, this is going to go further into the nebular phase. I'm not going to talk about the nebular phase today. And I mean, at some stage, obviously, this photospheric assumption breaks down. And specifically, what Ken has shown, like, we need to think about other effects. But specifically, what I want to do is take a spectral time series, which I'm going to call data vector, because I love math and vector symbols, and try to infer an explosion model. So in this case, it's only a one-dimensional model, and we have, like, different shells. We can think about this having different shells, let's say 20 shells, and then essentially we have a model. So, like, we have the iron abundance in the core, iron abundance in the first shell, the second shell, and so forth, and so sulfur abundance, and like all the different abundances. So when we think about this, this is, let's say, a 200-dimensional model, which is not something that astronomers sort of are used to. And, like, I'm not gonna go there now, but I mean, this is, in theory, this is what we want, right? So inferring the model from the data. So, and now I'm gonna do a brief detour to Bayesian statistics. I'm not gonna do it the fun way. I encourage you to read this book where it's the fun way. I'm gonna do it the boring way. And so we're gonna quickly talk about, like, what does this mean? So essentially we have a model. In this case, we will have a rate of transfer model, which has, again, the abundances as input, which then makes a spectrum. And so we want to know, given the data, what is the probability for the model at different points, like at silicon 0.2, silicon 0.3, and so on and so forth. And so this is proportional to, so my statistics colleagues don't crucify me, it's proportional to the likelihood, which is a metric that you compare model to data. And we already do this in our head. So when we look at the two wiggly lines, we sort of say, like, this is good comparison or not, because we sort of put physics intuition on this. And we also have prior assumptions about the model parameters. And so one of the prior assumptions that we sort of have is, like, we can't make 2 solar masses of titanium if there's only 0.6 solar masses of white dwarf, sorry, 1 solar mass of white dwarf to explode. Like, this doesn't physically work. This is essentially what we can sort of put in there. And so this is not my work. This is work by my student Jack O'Brien, who is, like, just put it on the archive, and it's in second review. And if the referee's in the room, thank you very much. Like, it was really nice referee report. And there's a couple of other people. I think none of them are in the room. But yeah, I mean, this is the group. And I also want to mention the TARDIS collaboration, who, like, without this would not be possible sort of to do. So what Jack did is essentially, like, not do the 200-dimensional space, because that would be crazy. And I mean, like, crazy comes a little bit later after impossible. So what he did, essentially, he just used one spectrum, a spectrum at t-10 days, so roughly around 10 days. And sort of, like, this is a simple case where we essentially then have a model, and we use the uniform model where we sort of just said, like, there's one set of abundances, and inferred the model. Inferred the model from the data. So we used SN 2002 BO at -10 days. One of the reasons was because I looked at this in my thesis, and it's always fun to go back to thesis work with people that are smarter than you and can do more than you. And so the other reason is because it's a prototypical 1A. It's the prototypical one. It's well observed and well studied. So we can look to others and see, like, what have they done right? What have we done wrong? And so we're going to do this at early phase where photospheric approximation holds. And if Ken doesn't yell at me yet, that means probably LTE is probably fine as well. Potentially. He can yell at me after. So the model that we use is our trusty TARDIS model, which is the TARDIS rate of transfer code. It's a steady state Monte Carlo code. It does a photospheric approximation. We have non-LTE in various forms, so we don't purely use LTE. We use nebula approximation from Lucy and the dilute LTE approximation from Lucy. And we can also do a full full NLTE for excitations, but we haven't done this here. And so we do line interactions and electron scatterings for now, and it's an open science code. So I mean, everyone can download it. Everyone can look at this and say like, no, you did things wrong there, TARDIS collaboration. This is wrong, and you should change it. And I mean, if you find something wrong, you can also change it, and then we'll credit you. And so it takes in such a model where we have sort of an inner photosphere and makes a spectrum out of this. So unfortunately, TARDIS takes a while to run. So for each parameter, and we have 14 parameters, for each parameter set, it takes roughly 5 minutes to calculate this. So this is way too much for even exploring a 14-dimensional space. I talked about the 200-dimensional space, but Jack was a 14-dimensional space. And so we found a clever way, and I'm going to talk about this later if people ask me. We found a clever way to sort of have a thing that essentially is TARDIS, but orders of magnitude faster. By essentially is TARDIS, I mean like the prediction uncertainty is less than 1%. So it makes spectra that are really, really close and takes the same input and sort of takes the same output. But whenever I say TARDIS, think we're going to use this. Just we need something faster. So the second thing that I'm going to talk about is the prior. Well, I should have said the first thing because prior is the first thing potentially. Anyways, the first thing that I'm going to talk about for statistics, the prior. And so we used, and I'm going to shout out to Fritz and group, the Heidelberg Supernova Model Archive, the HASMA data set, which is a super nice open data set of explosion simulations that I encourage everyone from the explosion theorists here to also make this, to put all the models out there to have open science happen. And then they have mergers, detonations, deflagrations, delayed detonations. It's a zoo of things that you can just look at, and like, you know, Fritz can comment on this more, and you can just download them. And so we could see what are the different combinations of parameters. So what we did is we looked at all cells above 10,000 kilometers per second to sort of inform us what different combinations there was. We cut out to 60% quantile as a bounds, just to make sure that we don't get like all crazy combinations, and we sort of stick within one data set, that we sort of stick within bounds that are physically realistic. And so we're treating the abundances in log space, which is not that important. But here's what it is, like just to jump in, like carbon to non-existent to 20%, sulfur from 0.5% to 20%, calcium from 0.05% to like 3%. So we have a range here. This is the range that we used as our priors, where we say this is what physically is realistic, because we don't want to search the entire parameter space. As I said, titanium, two solar masses would be crazy. And I'm really running out of time. This is quick. We also looked at the explosion, the time of explosion from 6 to 13 days, and we had an alpha parameter where we allowed the slope to vary, the slope of the density. So it's b to the minus whatever alpha. So this is in total like 14 parameters. And then the next step is like, somehow you need to compare a model versus data. We normally do this with our brains, but I mean, like to do actual likelihood, we need to go in and we need to calculate a number. And so this needs to incorporate the thing that we do in our brains where we say like, oh, TARDIS is bad here, and like we should only look at the lines. And because we know models are not perfect, so we need to think about this. There's intrinsic effects like the photospheric approximation, where you have things shining through above, I don't know, 7,000 angstrom. And so we need to like disregard this. And there's like extrinsic effects such as dust, which we all hate. The planet people love it, but we all hate. And so we thought about comparing this in a different space. And I think that is one part of this work that Jack did that is super important, but is probably underappreciated. So he went and he sort of used a technique similar to SNIT to sort of put the spectra in a space where line depth and shape matter much more than anything else. And then he also scaled the uncertainties to capture systematics, and I can talk more about this later. I'm just going to show a quick picture of what this is. So we have like Dalek or TARDIS. I mean, just think about Dalek as a fast TARDIS, and we have the transformed part. So then we had to sort of sample this space, and like to just quickly go back. These are the components we have, like on the fast TARDIS. We have our likelihood, which somehow gives us a number from like a spectrum, an observed spectrum, and a synthetic spectrum, and we have our prior, which is our HASMA models. And so for each one of the 14 dimensions, for each point, we now need to calculate a likelihood. And there's clever ways to do this, like, involving like, finite integrals and things like this. Essentially, we used a nested sampling algorithm to map this entire space. So for each one of the points, for each one of the 14-dimensional points, we essentially calculated the likelihood. And so the results are, this is the full posterior of a fit for SN2000-2PO, and you will say, Wolfgang, you can't read the labels. What are you doing? Don't worry about this. This is just to show you what you get out for a fit. And so for 200 dimensions, it will be 200 times 200. So interpreting these fits will be much, much more difficult in the future, like, because they're actual posteriors. And so we can sort of look like, this is a likely part of the parameter space. This is an unlikely part of the parameter space. Really running out of time here. So on the spectral fits, let's have a look at this. I'm sorry about the colors. They're not colorblind friendly. We'll fix this. We have SN2000-2PO at -10 days. So we have the green line, which is SN2000-2PO at -10 days. And so then we can look at the mean of the fits. This is sort of the top of the posterior. And you can see how well it fits or how well it doesn't fit. I think I'll let you judge this. The next thing that we can see is we can also see we have a best fit. So we have the max. This is where the maximum likelihood is. And then you can also see bands, like how well can the model adjust itself to sort of like, capture the data. And I think this is the unique thing. We don't look at one model, but we look at like how good is the model overall. And so I think this is the power of this, really the power of this method. And so in the last 2 seconds, I'm gonna take a minute, if that's okay, to explain this. It's a rather complex plot, and I'll see if this goes in a minute. So this is essentially the projected posterior of all the different abundances. So this is 12 abundances. So if you look at the black histogram, this is the posterior. So it gives you the probability of the model given the data. And so, for example, for magnesium, we can see this is not well constrained from 10 to the -4 to 10 to the -3 or 10 to the -2. And this is the power of this method. There's no like, oh, this model fits, but we can say like, no, magnesium is not a good indicator. And we can actually, this is an actual probability. So we can also compare our results to other people because like, oh, we want to keep ourselves honest, at least when someone's watching. And we're comparing it to a full tomography, which was done manually, but does not have these uncertainties. And so as this is difficult to compare, we used like a range between 10 to 15 kilometers per second to sort of compare in that range and then plot that on there. So this is the gray bars, if that makes sense. Sorry, that should have circled the gray bars. And then we compared to the hazmat deflagration and hazmat detonation, which is the green and the orange. Again, sorry about the color choice. And we can sort of see that for quite a few of the important element tracer, the detonation is a good measure. So at -10 days, detonation seems to rule, but unfortunately, like we sort of half knew this anyways, because delayed detonation is detonation on the outside and pure detonation is also detonation on the outside. So we can't tell you if it's a single or double degenerate, even though I hate these terms. Anyways, this brings me to the conclusion, which is it's a new way to do supernova tomography. It is the first probabilistic reconstruction of type 1a supernova. And doing this allows us a current direct comparison between spectral time series and explosion models. So we can take data and actually make something that we can directly compare to explosion models in a probabilistic way. So SN2000 looks like a detonation from the outside with caveats, and the maximum likelihood will mislead you. So just making one model and sort of, I mean, I think you can make a model and say like, oh, this model is definitely not supported. But if your wiggly line looks like the observed wiggly line, you can't necessarily say this is the explanation. So the next step is many more supernovae. Now that we have a hammer, we're just looking for nails, right? And we do sort of multi-zone models. And in the last 15 seconds, I'm going to thank you for listening to me, but I also want to make sure that this is an open science code that we're using. So many people, many more people that are on the paper are contributing. We have 100 contributors to TARDIS. So TARDIS is developed by an interdisciplinary team of various cultural identities, beliefs, and gender identities of very, very diverse set of people. And these are just some of the people here. This is the core team. And so when you use TARDIS, and there's many more, in total, we have 100 contributors. Please also cite the Zenodo link if you use TARDIS, just to be sure to make sure we credit everyone on there. And so I think on this thing, I'm going to stop and I'm going to apologize that I didn't stick to my own rule, Bob, but maybe I have a 30-second window for a question. Maybe there are no questions.
I'm sure there are questions. Thank you for the excellent talk, Wolfgang.
Thank you.
Wolfgang, I have a question. When you did this comparison with 2002 BO, and you derived that the detonation was the best model, I wonder whether there may be a bias in the fact that you may not have enough deflagration model, Chandrasekhar deflagration models. It seems that they are the probability for those is quite narrow, and I wonder if it is so narrow for this kind of model, for the deflagration models, because there are a few models, many less models than for double detonations or so.
That is an excellent question, Pilar. So just to be clear, so we used all the models. So there's delayed detonation, which is the deflagration and then detonation, and we used pure deflagration, pure detonation models. So we used all the models to make our prior, which hopefully we can see here. So we consider, sorry about this. We essentially consider all the models that Anna has my data set, mergers, detonations, deflagrations, and delayed detonations. So for now, we cannot rule out a delayed detonation. So a deflagration detonation transition. We're not ruling out a 1.4 solar mass textbook classic scenario. We're just saying the outside look much closer to detonations than us. And so Fritz, Fritz's team who's put this stuff together, I don't know if, I mean, he would be able to comment more on like, what parts of the parameter space we might be missing. But yeah, it's a good question. So we made sure that we really capture the whole breadth. I hope that answers your question, Pilar.
Yeah. Mm-hmm.
I see Ken has his hand up. Time for a quick question.
I think it's a quick question. So when you make the priors for the abundances, say, I don't know how to word this in a mathematically rigorous way. Are the priors independent? As in, let's say you have a detonation model and you produce a lot of nickel, you're not going to produce a lot of silicon or something like that. Yeah, so are they independent in that sense?
No, this is a very good question. So originally I tried to do this, but it's really hard to sort of sample in this huge space, and I can go into many more details about this. So in the end, we played the same game as sort of the supernova models of the ancient supernova models like Hachinger and Mazzali did, and we sort of used oxygen as a filler element. But other than that, other than using oxygen as a filament element, we sort of stuck in this just uniform between them. We thought about going in where we sort of say if you make more silicon, you make more sulfur. We thought about doing this, but then we thought we try the simplest thing first. And I think that is potentially a really good thing to do in the future when we do multi-zone models, because then we can cut down our parameter space, because we don't need to explore the full square of silicon versus sulfur, because as you said, there's correlations in this parameter space. But this was sort of a first simple attempt at the methodology, and I never thought we would get signs out, but we did. So this was the stupidest thing possible we could do, and it worked. But in the future, specifically for multi-zone model, we need to do exactly as you say.
Excellent. Thank you very much, Wolfgang. Moving on, I think Abigail's up next.
All right, let's see if I can share my screen correctly. Can you all see this and my mouse?
Looks good.
All right, great. Well, thanks for having me. I'm Abigail Pullen. I'm a postdoc shared between Carnegie and Caltech right now, although given the pandemic, I've never actually gotten to step foot on either campus as an employee. So looking forward to that changing in the near future. We've heard a lot today already about the double detonation. This is the wrong slideshow, I think, actually. Sorry. No, it's not. It's the right one. My bad. We've seen a lot of talks already about the double detonation channel, so I'll go through this very quickly, but I did want to reiterate a point that Ken made earlier of, for this double detonation subchandra channel, we can have varying types of companions. For all of them, the idea is that we have a subchandra Sekar mass carbon oxygen white dwarf, which has gained itself a shell of helium. Either from a non-degenerate companion like a helium SDB star, in which case there's going to be a lot of helium on the surface of this white dwarf. A degenerate, another white dwarf companion will end up with a small amount of helium on its surface, or these D6 mergers that we heard about earlier can result with a very, very, very little amount of helium on the surface of this subchandra white dwarf. But in all the cases, the hope is that it's far easier to ignite helium than it is carbon or oxygen. And an initial helium ignition will send a shock, will burn around the helium shell, send a shock front into this carbon oxygen white dwarf, and then it can compress that carbon oxygen, get an ignition, get a thermonuclear runaway, like a traditional type 1a supernovae, hopefully, or not. So I have a preliminary 2D movie. You've seen a couple of these today of what this looks like for a lot of helium on the surface because it's easier to visualize. But here's that initial helium ignition. You can see it burning around the white dwarf, and you can see most easily in this temperature profile, the shock front traveling towards the core of the carbon oxygen white dwarf. Where that converges, you get the thermonuclear runaway. If we break this down further into composition here, so we have density on the left, radioactive elements, so this is nickel, chromium, iron, anything that decays and releases photons, and intermediate mass elements in green here. And as we can see pretty quickly, as this helium shell burns, we end up with a lot of radioactive and intermediate mass elements on the surface of ejecta that wouldn't be there for a Chandrasekhar mass explosion. And so I looked at it as my job to try to ask the question, kind of agnostically of progenitor, just as a function of the white dwarf mass, of the shell mass, and later going back and looking at where that shell would come from. What is created out here and how does it affect the observable properties of a double detonation explosion? And can we try to pull these out of our populations of 1As? I do want to note that that's an early movie. This is what I'm doing now, what it looks like for this 2D kind of hydro time series. But all the results I'm going to show you at this point out are not these beautiful 2D movies. They're from our published 1D models. So just wanted to be very clear on that before transitioning into the radiative transfer. But as I alluded to earlier, the observable properties of these double detonations, and as we've heard throughout the day, are really dependent on how much helium is on the surface of the carbon oxygen white dwarf. In the case where we have a degenerate companion, where for these thin helium shells, we get something that at least qualitatively first glance here looks like a type 1a supernovae. We get a smooth rise to a nickel powered peak that occasionally or eventually decays into a cobalt powered tail. But in the case where we have a really large helium shell on the surface of this subchandra white dwarf, we create a lot of very heavy and very radioactive material on the surface of the white dwarf, and we start getting bizarre early features created by this material. So in the light curves, you can see this bimodal light curve, basically, of this early peak that we would not expect, especially in this extreme, for a type 1a supernova. And that's created by the fact that the shell burns itself into radioactive material. So you're releasing photons from, it's mostly chromium actually, rather than nickel, at the very edge of the ejecta. So it has a very short diffusion time for it to escape and create this early peak that you'd see far before the nickel powered peak. So I think we can all agree this doesn't look like a type 1a supernova. That's not revolutionary. We've known that the huge helium shells didn't look like type 1a supernovae since the 80s. But the same story holds true for the spectral story of this is our models plotted with the heaviest white dwarf on the top, the lowest mass white dwarf on the bottom. So this will also correlate to brightest event to dimmest event with the thin shells over here and the thick helium shells over here. And the same story becomes true that these guys, at least qualitatively, first glance, look like type 1a supernovae. We see the trends we want to see here, where the brighter the event, the shallower these intermediate mass element features are. We see things like titanium showing up in the lower luminosity events, but in the thick shell explosions, double detonations, we get this crazy amount of line blanketing from the thick, optically thick helium shell ashes that are sitting on top of the explosion. And this line blanketing feature exists up through peak. And I'll say here, these are LTE simulations done with Sedona. So I'm not going to show you any data past peak with this method, because as we've heard from Ken, we can trust this up until around peak luminosity, but especially for these lower mass explosions, they expand very quickly. There's not a lot of ejecta mass and they become optically thin pretty quickly. So we don't want to look past peak with LTE methods. But let's focus, we're talking about 1As first. So let's focus on these thin helium shell models. I've already gone over how, at least qualitatively, these show the trends we want. But an important thing we noticed while plotting this up in this manner was that as we increase the mass of the white dwarf or the luminosity of the event, we notice this relationship where we also, if you look at this silicon 2 line here, we also get a relationship between the velocity of this line and the luminosity of the white dwarf. And this makes sense on surface level because the kinetic energy is a function of the white dwarf mass, which directly controls how much nickel is created. So that'll translate to velocity, to luminosity. The velocity is just that nickel kinetic energy and the binding energy relationship, which again is just a function of the mass of the white dwarf. So this should be a pretty traceable function for these subchandra mass explosions. And so we decided to ask ourselves, okay, if this is a relationship that exists in the subchandra explosions, do we see them in real observed type 1a supernovae? And the way we tried to do this was taking this set of observed type 1a supernovae from Zhang et al. 2018, which were all of the type 1a supernovae in their observed data set that had resolved rises. So we plotted them here. This is peak B band magnitude on the y-axis and the velocity of that silicon 2 line on the x-axis here. And when we put our models on top of them, we start to maybe see a picture emerge where at least the machine learning tools of our eyeballs say, okay, well, it looks like there might be two groups of supernovae here, right? These guys, which follow the relationship both on the low silicon velocity end and the high silicon velocity end that we expect from these modeled double detonations, and this cluster that sits above this relationship. And if you do just the simple kinetic binding energy relationships and say, okay, well, if this guy has the same amount of nickel as this guy, this cluster does sit right around the Chandrasekhar mass limit. But this is pretty, small number statistics, not good enough on its own. So we continued to ask, okay, is this us beginning to see two different groups of type 1a supernovae or not? Will they separate themselves on just this, or on other axes as well. So the first thing we looked at was through the same data from this Zhang paper, color. And this is B at Bmax minus V at Vmax. And again, these two groups start to look different, where this cluster is significantly bluer than the group of supernovae that follow our models or any of our models. And we expect these events to be intrinsically redder because even for the very thin helium shells, as been mentioned throughout the day, there is a little bit of ash on the outside of these explosions, which will redden the events. So perhaps what we're seeing here is that these events are intrinsically redder than these events, subchandras, chandras. That's all I pulled out of the photosphere features. But digging into this further, I decided that LTE wasn't enough. I wanted to look at the features of these double detonation explosions in the nebular phase, so 150 to maybe 400 days after explosion. And to do this, you can't just use LTE methods. I had to use Sedona to calculate the energy deposited throughout the supernova ejecta's lifetime, and then use our nebular companion to Sedona, Sedoneb, which can take this Sedona data and then do a snapshot in time full NLTE calculation to make a nebular spectrum. So these are our results here, and this is the same kind of pattern I've been showing before, where the heavier white dwarfs, the higher luminosity events, are plotted here down to the low luminosity events. And we can go ahead and put a time series, or not time series, a population of real observed type 1a supernovae in the same order, where these are the brightest events, these are the dimmest events. So this is a 91T here, 11FE is fairly normal, and these are two subluminous 91BG-like events. And we can see that again, the qualitative trends continue, where we have broader iron lines for the brighter events that become narrower as we lower in mass. And the really interesting thing that started to pop out of these double detonation models was this calcium emission line, that as for all of our models, we kind of overproduce calcium compared to most observed events. But it becomes very prominent as we go down in mass for the underlying white dwarf. And these are all, again, the thin shell models. So this kind of looks, like a 91BG. We have narrow emission lines here. We do have more contribution from calcium. But I'll point out this bottom event here is not a type 1a supernovae. It is a calcium-rich transient. And this was a total surprise to us, that as we got to the very, very low end of the white dwarf masses, we stopped seeing things that looked like type 1a supernovae and started seeing things that looked like calcium-rich transients. And I will say very clearly here, I am not saying that the double detonation progenitor channel creates calcium-rich transients, but I am saying we can learn something very interesting about these calcium-rich transients from these results. In that, so just a reminder, since we haven't talked about these today, calcium-rich transients can look pretty different in the photospheric phase, but in the nebular phase, you pretty much just see this calcium emission line. To be calcium-rich, the calcium line has to be over the oxygen line has to be greater than 2, the ratios of those lines. And there's been a lot of argument about how much calcium is needed to make this kind of behavior happen. In literature, I think the original event said something like 50% calcium. And what I'll point out that is important to learn about these guys is that we don't need that much calcium to get a calcium-rich event. So in these low mass double detonations, we're looking at 1% calcium in the ejecta, and we're seeing only a calcium line. So this is kind of my current obsession, actually, rather than 1A's, is the calcium-rich transient side of things, of what can we actually learn from a calcium line. But this is a tangent, so I will move on. I wanted to go back and look at this parameter space of magnitude versus silicon velocity with these nebular features, specifically looking at the ratio of that calcium line to the iron 3 emission line. But it turns out in our original data set, there are not enough supernovae followed to the nebular phase. So I had to go and pull from all of the public data sets, and I got maybe 30 type 1a supernovae that had a spectra at peak and a nebular spectrum at the right phase. So this isn't great. Okay, thank you. I'll go very quickly now. They color themselves again in two separate groups where calcium, the supernovae that follow our proposed relationship do show stronger calcium features than those that sit in this cluster. So this is about the fourth axis now, where these start to distinguish themselves. The one we're working on now is I have a summer student working on coloring this parameter space by carbon absorption features, because we don't expect a lot of carbon to be left over in a double detonation explosion. But very, very quickly, if you were to believe me that some type 1a supernovae are created by this double detonation channel, there's a really important question that you should ask. What about the thick shells? Because we know that these binaries exist in nature, right? So if this mechanism can explode a white dwarf, we should see these. And until very recently, we hadn't. But just jumping the gun a little bit here, in 2018, we found with ZTF 2018 BYG, or ZTF Aquazu, which had these smoking gun signatures that we expect for the thick helium shell double detonations. We get an early excess in the light curve and line blanketing up through time of peak in the spectrum. So I worked with a graduate student who I think is now starting a postdoc, Keisha Day, to characterize this event with our models and their observations. I had him send me the light curve, and for one light curve, I can give you one model that will fit it, because this early peak is determined by the mass of the helium shell, and this secondary peak, the mass of the nickel. So our model that fit it was a 0.76 solar mass white dwarf with 0.15 solar masses of helium on its surface, which is a huge amount of helium. And so this is our best fit for the light curve. I sent this to Keisha, and he sent me this back of the fit to the same spectrum. And this is the plot that Shrab showed at the beginning of the day of what I would call the most direct evidence that this mechanism can ignite a white dwarf. And then we should be taking this seriously of looking for them amongst our type 1a supernovae. This is our our pilot event, say, our first one, but wow, okay. But since then, we found one definitely more, maybe another one. So 2016 H and K, again, we get a great spectral fit. The nebular spectrum evolves to just being calcium rich. And then this new event, 19 YVQ, is still being debated. But it does have the early excess and the strong calcium emission we're looking for. And so I'll leave this there and hopefully take some questions.
Thank you, Abigail. That was a really great talk. Yeah, it's a tricky one. I see Mario has already put up his hand.
Yes, thank you, Abigail. Very nice talk. I wonder if you have explored a little bit the infrared properties of the type 1a supernovae, particularly the light curves, because there's so much information there, the first maximum, the second maximum. So perhaps that could be a great diagnostic in order to separate these two potential populations.
I agree, and I haven't actually done much in that yet, but I have a Magellan program 2 nights where we're at least in the nebular phase going after both optical and near IR spectra in the nebular phase. So we're hoping to start digging out in that regime as well, but I don't have anything to say about splits there yet.
And I also see Ken has his hand up.
Hey, thanks for the great talk. So I had a question about the correlations between the peak magnitude and the silicon velocities.
Yep.
So as you saw, I also had that same plot, but in multi-D, it looks extremely different than in the 1D case.
Yeah.
And so, you know, we don't find that tight correlation. We find a big, much larger scatter.
Yep.
One other thing I wanted to say is that in the Zeng Zheng sample, it is a relatively small sample. When we
It
looked
is.
at the Burrow sample with CSP, there wasn't any evidence for two separate populations. Everything was just kind of filled in.
That's not quite true. So in the Burrow paper, there's definitely more fill between the two groups, but they, at least with Gaussian processing, kind of decide there are three groups. And I argue that if you could, with that Gaussian processing, fit a banana shape instead of just Gaussians, that would still look like two populations. For the 2D question, yes, and this is a.
I'm wondering if you've actually seen that in your 2D
cross
results.
it
Have you had a chance to look at your 2D results?
I only have one 2D model where I finished the radiative transfer, and it's like our most spherical case. So I'm not ready to say anything, but no, I don't see that kind of spread, but that will really depend, as you know, on where that carbon oxygen convergence happens and how aspherical the explosion is. So I have a really low mass, pretty spherical 2D movie where no, I don't see a huge spread. It looks pretty spherical, but I'm not ready to say for the whole parameter space whether or not this falls apart.
Okay, thanks.
Mm-hmm.
Excellent.
I have a question, Abigail. I don't know. I think this is probably something that we can come back to it on Thursday on the use of the cosmological samples of 1As for the determination of H0 and also the dark energy, because of course then having these two clusters, one wonders if this has been seen by the Carnegie supernova survey and by other many collaborations that have a large sample of 1As, if they see also this kind of clustering. So
Yeah.
that
Yeah,
would be
so,
that you attend that session on Thursday.
yes, definitely. So the data set that Ken and I were just talking about is the Carnegie supernova data set, where there is clustering, but not as much of a gap between the two of these. I will say for cosmology, this population up here has always been mildly problematic because they are too red. And so we've had to invoke things like extra dust extinction to make them fit our Hubble residuals. And I'm hoping that we can develop this to a place where perhaps if these guys are intrinsically more red, that it's a better, we have a better way of standardizing them rather than just saying, okay, these ones have to be in a dustier environment for a reason we don't quite understand.
Mm-hmm.
Excellent. So there's a small adjustment to the schedule. I think we have one final short presentation from Sylvia.
Hi.
Hi. I'll give you a 1 minute notice. It's just 5 minutes. So after 4 minutes. Oh, you can just put it on full screen and go ahead.
Oh, wait a minute. My PowerPoint.
I think we saw it momentarily. You can.
Yes, I have a problem with PowerPoint that is not sharing with Zoom.
PDF? Can you do?
I have to save in PDF. Wait a minute. Now you can see.
Yeah.
Yeah, if you can put it on full screen. Yeah, there you go. Perfect.
So thanks, I would like to thank the organizers for the opportunity. My name is Silvia. I'm from the Technological Institute of Aeronautics, ITA, in Brazil. I'm a PhD student. My advisor is Professor Manuel Malheiro, and my co-advisor, Professor Judel Domingo. And today I'm going to talk about charged polarized white dwarfs with neat temperature as a possible source of type 1a supernovae. Okay, this is not. So here we go. There are some superluminous type 1a supernovae which have been related to supermassive white dwarfs. This is white dwarf with masses above the Chandrasekhar mass limit. There are works that consider white dwarfs with a magnetic field or charge as a crucial role for the interpretation of superluminous type 1a supernovae. So in this work, we are going to study the properties of polarized charge in the structure of white dwarfs. There are several works that study charge in white dwarfs. For example, this work from Liu and collaborators that study the charge density proportional to the mass density. And this one, more recent, from Carvalho and collaborators that study a surface charge density. But these works find the electric field outside the white dwarf, something we avoid creating a polarized charge in the structure. So here's the equation of state and the structure we are going to use. The equation of state, the pressure have the component of electrons, nucleons, and photons, and the energy density also. So we consider in the core a constant temperature, and in the envelope, we create a temperature distribution. So for the structure, we use Heisner-Nordstrom metric to get these equations and describe the inside the star. So here is the novel, The Charge Density. We are inspired by this work of Negreiros and collaborators. So we consider charge density, a polarized charge density. Here's the term of a positive charge and a negative charge. These K plus and K minus are normalized with the total charge that we consider 0. And this is where the charge are located. This is a positive charge and a negative charge. So here's the first result of a single star with the energy density of 10 to the 10 and a center temperature of 10 to the 8 Kelvin. So here's the charge density as a function of radial coordinate for different polarized charge. So we can note that inside the star, we have no charge density. And then in the surface, we have a first Gaussian, the positive charge, and then another peak due to the negative charge. And then it equals to 0 again in the star surface, and consequently at the outside the star. So with increasing the polarized charge, we increase these peaks too. So here we plotted the pressure as a function of radial coordinate for these stars. We have a typical white dwarf behavior for the pressure. The pressure is higher at the star center, and then it decays until the end. So here is where the polarized charges are located. So we have a peak due to the positive charge, and then decrease when the negative charge is reached until it reaches P equal to 0 at the star surface. So this behavior has a consequence in obtaining larger and more massive stars. So here's the electric field as a function of radial coordinate for the same star as before. So we have no electric field inside the star, and then we have a peak due to the polarized charge in the surface. So higher the charge, polarized charge we choose, higher the peaks. And we have no electric field outside the star. So here's a sequence of stars with central temperature of 10 to the 8 Kelvin. This black curve shows the uncharged star. The uncharged star is a typical white dwarf with a maximum mass around here. But for the polarized charge, we do not found any maximum mass. We find this divergence specifically where piconuclear reactions and inverse beta decay happens. But for stable configuration, we found masses around 2.2 solar mass, which is a value above the Chandrasekhar mass limit. And this curve is very similar to the ones obtained recently by Otoniel and collaborators for supermagnetized white dwarfs. So here we plotted the mass in solar mass as a function. Here, not radial coordinate is the radius. The star radius for several sequences of stars. So here again, for uncharged star, we have a typical white dwarf behavior for the mass. Here's the maximum mass. And then for charged polarized stars, we have a shift upward of the curves. So this divergence we associate it to the high polarized charge we give to the star. And we also obtain masses above the Chandrasekhar mass limit. And for the first time, we found masses above the Chandrasekhar mass limit for charged stars with no electric field in the outside. So we used a realistic model for white dwarfs with near temperature in general relativity. And we found massive white dwarfs with not main electric field in the outside. So this white dwarf may be considered possible candidate for super Chandrasekhar white dwarfs, contributing to our understanding of the type 1a supernovae. And our curves are very similar to the ones obtained for supermagnetized white dwarf by Otoniel and collaborators. So this is, thank you.
Thank you, Sylvia. We have time maybe for a short question. I think Wolfgang has his hand up.
I do. I have a very short question. So you have presented an interesting model. So I'm wondering what observational signatures would rule your model out?
So this work is still in progress, but we will observe the luminosity of the star. With our models, we will compare it.
Yeah, but I mean, that can be explained by other things as well, like rotation or something like this. I'm wondering what is a specific thing to your model that would produce observations that could be sort of ruled out, or could rule out your model? Would we see polarization or like Faraday rotation or something like this?
So for now, we can only have luminosity in our models due to the envelope that we are modeling. I didn't listen well. You said rotation.
Faraday rotation, yeah. I mean, you know, due to strong magnetic fields. I mean, I don't know. I'm just trying to understand this model. What would be an interesting measurement to sort of look at this model in more detail?
So this model is still in progress, so we don't have enough properties to compare. But we think if we have enough time to look for luminosity, we have a better answer for your question.
Thank you so much. Very interesting work.
Okay, I think in the interest of time, we can move to the panel discussion.
Maybe can I ask a question? Can I make a comment?
Sure, please.
Yes.
Manigoto here. Yeah, just for comment, nice talk for the speaker. Actually, previous speaker, I'm commenting. As Manuel knows, actually, for as long as magnetic white dwarfs and massive white dwarf based on magnetic field is concerned, Manuel knows very well. Basically, we started since 2012. So you keep telling no that arterial work. That's a fantastic work, of course. But as long as magnetic field based massive white dwarf is concerned, that is not the first work. And the second comment is that if I am not mistaken, for charge white dwarf giving rise to massive progenitor or whatever, I think Czech group attempted earlier, group of Trulich, and first author I think Believ, if I am not mistaken. That's all.
Okay, thank you. So,
May I make a comment?
well, we're almost out of time. We have only 14 minutes out of, I think, the original 45 for the panel discussion. So I would like to move on to the panel section.
Okay.
Thank you for all the speakers. And let me just go ahead and perhaps share the questions that we had listed. And I think everyone can sort of pitch in, but maybe we can start with the first question, which I think we've had a number of contributions about, which was, what unique observational signatures exist to discriminate between type 1a progenitors and explosion channels, sub-Chandrasekhar versus Chandrasekhar models? We've heard a lot of discussion, and anyone can feel free, speaker or not, probably to pitch in on this.
I find that it's very interesting to see, and this will be very important for cosmology, if we have a real separation, a real gap between all the sub-Chandrasekhar explosions and the Chandrasekhar ones, or we are able to find some continuity within these. Because I was very interested actually by Abigail's finding, and in cosmology normally one sees a continuity, but I wonder whether from models we can say it's gonna be a gap or not.
Well, I think we showed today that, even within the field, there is still debate about this, but I wanted to clarify that, I do think there is going to be overlap where it's going to be very, very hard to tell what is sub-Chandra and what is Chandra. I just want to be careful when we say gap, that has been mentioned before, the plot I showed of the two populations, the actual gap between them fills in, and so that will be a very hard area to quantify. But I am of the opinion that there are definitely two groups of progenitors for these systems.
Yes, Fritz, and folks, I think, can just feel free to unmute, have more natural discussion.
Yes, I mean, of course, this is a question that we have thought for quite a while in the community about, right? The distinction between different explosion models. And I think all the different measures that we came, or different measurements or different characteristics that we came up with really don't tell us the difference very clearly. I mean, this is true for the manganese argument with the nuclear synthesis, right? I mean, now you actually see that also in Sub-Chandrasekhar double detonation. So there's no clear distinction. And also, Abigail, I found it very interesting with the silicon velocity. So I remember that Markus Kromer and Rüdiger actually looked into this a while ago as well with Stefan Taubenberger, and I think, but they never published anything about this. But they looked into this. But I think you actually find also such a relation for the Chandrasekhar explosions, right? I mean, this is actually sort of, it's always kind of generic that if you have brighter models, then you actually have higher explosion energies, and then you have higher velocities, right? So that's actually something that you find in all explosion models, but it's not really there in the data, and that's quite puzzling. So, I mean, finding good ways to distinguish between the models, that's, I think, one of the big challenges. And I really don't see how, whether we have a good handle at the moment.
Hi. I have a question actually to Fritz. I found this manganese debate, I always found like one of the super fascinating ones, like, with Evo starting sort of like all this and saying like, look, I mean, in the pre-solar grains, we actually have a different abundances. So this is not only cell abundances, but this is actually physically measured stuff. And so, I actually should also mention, we should call them near Chandrasekhar models, because I think we confuse people that they're actually at the Chandrasekhar mass, and so my question was, what has changed? I didn't quite capture your argument. Might be because I didn't pay attention properly. Fritz, why are we now suggesting that there is enough manganese being made in the double detonations? Like, what has changed from before? And this is my ignorance more than probably you explaining.
The argument that was before actually about the manganese that you produce in the carbon detonation, right? And there, of course, with the sub-Chandrasekhar mass models, you don't enter the regimes where you produce a lot of manganese, but you actually do produce cobalt-55 and manganese at the helium shell detonations. And if you take this into account, that also these sub-Chandrasekhar mass double detonations would contribute quite substantially to the manganese over iron ratio. And that's why, as long as you actually sort of say that the sub-Chandrasekhar mass explosion models are double detonations, then I think they will also contribute to the manganese, right? I mean, this is
okay. It's so, like, this is again my ignorance showing. So I understand it, as far as I understand it, like, in the high density regions, you have high neutralization happening, and you make a bunch of iron 55, which then decays to manganese 55.
No, the point more is that actually it's not actually sort of a neutralization effect in the first place. The point is mostly that we made back then is that if you have whether you have alpha rich or normal freeze out from NSE, and that was sort of with the Chandrasekhar mass and sub-Chandrasekhar mass models. So in the sub-Chandrasekhar mass models, you have normal freeze out from NSE. In the sub-Chandrasekhar mass models, you have alpha rich freeze out. Alpha rich freeze out means that you have lots of light particles actually when nuclear statistical equilibrium freezes out. Then you have cobalt-55 P gamma reactions that just produce another nickel 56 out of that, right? So it's gone, and then you don't produce manganese. So that's actually the mechanism there. It's not really about the neutralization. Of course, that also helps to directly produce a manganese, and there's a metallicity effect in this too. But the primary effect that we actually back then thought of was the destruction of cobalt-55 in alpha-rich freezer. But of course, the double detonation models, there you produce the manganese actually in the helium shell detonation. So that's a thing that was not considered in the models before, because we focused on the carbon detonation there.
So,
and also, I don't know if Ken wanted to chime in or speak on a different issue.
I did want to speak on a different issue, but I also wanted to add to what Fritz said. In addition to the helium shell, there's also, if you go to slightly lower masses, say 0.95 or 0.9 solar masses, you do actually produce a lot more manganese to iron in the incomplete silicon burning. So even without the shell, if you go to slightly lower masses, you are able to get more manganese.
Yes, and in particular, you're interested in the manganese over iron ratio, right? So then you produce less iron in the explosion, and then actually sort of this ratio. It's always the ratio that's important here. It's not actually the total amount of manganese you're interested in. It's the manganese over iron ratio that you produce in these events.
If Wolfgang's done, he's gone now. Is it okay if I share my screen? I wanted to speak to this peak
Sure,
magnitude.
I will stop sharing this. I don't think it's too much to share.
I showed this plot, but there was a lot of stuff going on. So I just want to remind people what we found with our 2D results. So this is the same plot that Abby was showing, but this is peak magnitude versus silicon velocity. And so in 1D, and we also saw this in 1D, our 1D simulations, we do find a pretty strong correlation that goes something like that. But in 2D, the different viewing angles, you get really, really different silicon velocities due to the asymmetric density distribution. So we do get a lot of these relatively low silicon velocity in the normal luminosity region. This is what looked like an extra clump in the plot that Abby was showing. So I'm pretty sure that in 2D, she will not recover the same simulation, the same correlation. She'll see a much larger spread. And Fritz, I assume that what you've been doing with Sabrina Gronau you're probably in the midst of doing a rate of transfer. I imagine that you're also seeing this kind of, you know, it's no longer a correlation. It's like a spread that covers the observations.
Yeah, and it may also be, I mean, the old discussion we had with Rüdiger and Markus, I think that it may be possible that back then they actually looked into the angle averaged things there. And that, of course, in the spread that he introduced by the asymmetry may matter here. I agree.
Mm-hmm. Yeah, it's also, sorry, this is actually a different version than the one I was showing. Most of the viewing angle is kind of located here. The viewing angle starts to spread out as you go to higher latitudes. So actually, if you were to angle average our results, they'd be more like here, I think. Yeah. So this is definitely a multi-D effect. We did not see this in 1D. Obviously, we didn't see the spread in 1D, but our 1D results were much more in line with what Abby was seeing. And it's only when we went to 2D that we see things that actually cover the observations.
Bob, perhaps we can answer the third and the fourth questions instead of going into the second. I just wanted to let you know that we can keep talking a little bit more than past 30. They are going to shut us off at 10 minutes past or 15 minutes past the hour. So past 7:30, so 7:45 we're out, definitely. I wanted to also to ask you to remind you that on Wednesday there is the Hubble tension session on the main channel, and on Thursday we will try to be on time to give some room for the roundtable. But we can continue now with this.
I see Wolfgang has his hand raised.
Yeah, again, so I mean here maybe a little comment on what are the prospects for direct model comparisons between the various groups and codes. There was a really nice effort for the rate of transfer part led by I think Stefan Blonder and like a couple of other people were involved in this, and so we were still wanting to do this, but then there was this pandemic. I don't know if people have heard of this, that didn't allow us to travel, and so but for the rate of transfer part, we're super interested. And one of the things that I'm very, very interested in is like, you know, the atomic data. I think like that would be really interesting to sort of see like how well do we actually know the atoms that make this whole shebang happen. And I mean, no, but I think there's some work going on in our group, but I think maybe other groups are doing some of this as well.
For instance, Bolwan, you are also in touch with Abigail in order to exchange
We are through Peter Nugent. We had a chat with Peter Nugent, and we have some, actually Abigail sent us some models to Jack as I remember. And we're at some stage, Jack was busy submitting the paperwork, then we'll go to your work, which is very nice, very, very nice work. And that killed the conversation.
May I add a comment on Fritz, the last statement? I think that actually the absolute mass of the manganese and iron are also important, because at the end, the actual mass goes to the total supernova rate, and then goes to the manganese production of the galaxies. So I think we still need to maintain a certain amount of manganese mass instead of just maintaining the ratio in order to conform with the observational data.
Sorry, I'm a little confused. At the end of the day, isn't it still, you're measuring the manganese on iron ratio?
Yes and no, but at that time when I model with Chiaki, so actually we have a sort of targeted, it needs to be at least about 1 to 2% of solar mass per a single supernova explosion. So it is. So we have, and then I find that it's because the supernova rate will scale down everything in the galactic scale, in the scenario of galactic chemical evolution.
Well, I mean, going back to the nucleosynthesis arguments, I think the biggest uncertainty that we have at the moment there is not only the type 1a supernovae, but it's the core-collapse supernova contribution there, right? I mean, there's big differences from what the models of different groups predict there, and that shifts up the GCE quite a bit up and down. And so therefore, I think this is actually the main uncertainty we have at the moment. So we can actually give homeworks to the core-collapse supernova community.
There's a related issue there, Fritz, I wonder about, which is in the last week or two, we've heard a lot about electron capture supernova events, and those are also supposed to produce a lot of neutronized isotopes and are highly uncertain. Is there any understanding as to what that channel might contribute to manganese, if at all?
Well, we had a paper on this. I don't really remember what we actually wrote there. Manganese, I don't think that this was a major thing there. But for the neutron-rich isotopes, yes. I mean, they can actually sort of make quite a can have quite an impact. And there was a paper that we had with Sam Jones like 2 or 3 years ago that actually listed all this. Yes. But I think the manganese contribution. I mean, these objects should be rather rare anyway, right? So
right. So it's only if they would really tremendously overproduce that they would contribute at all.
I have a question for Ken. You have looked through Gaia on these very hyper velocities white dwarfs as part of your D6 scenario, but I wonder whether you're planning also to look for other type of stars, so some subgiants that may be a little bit modified by the explosion of the supernova that may blows part of the upper layers and may look a little bit peculiar, or yes, also main sequence stars. They can have, of course, they will have less velocity than the ones that you are finding, but I think they are also interesting. In my case, I'm trying to now to follow some of the supernova remnants, and I have some candidates that I'm observing right now that are moving at 350 kilometers per second, and they don't look like white dwarfs. Some supernova.
Yeah, the only cuts we did were looking for velocity, so that was the only indicator that we were looking for. We did do some searches deeper in supernova remnants, but we didn't find anything that was moving that fast. And obviously, you and Wolfgang have lots of experience looking at spectra inside of supernova remnants. Wolfgang is cracking up. I think that's very funny. But yeah, in terms of our Gaia search, we were just looking for the D6 stars, and those had the signature being very, very fast. So that was the only constraint we had.
Maybe on that note, we found a halo star that moves at, I don't know, what was it, 400 kilometers per second, right in the center of RCW86, which is exciting. I think, like, you know, halo stars and supernova remnants are underappreciated, and there was lots of excitement. And then we had VLT time, and unfortunately, it looks like a low metallicity star. But yeah, it was very fun for a while.
But that even if it has low metallicity, it may have lost part of the surface. Maybe.
I mean, all of this is true, but I mean, you know, like, given sort of the Occam's razor, it moves at a high velocity in the supernova remnant, but it looks so close to a halo star that I feel like it could be. Of course, you can always make an argument that it could be the companion, but I think it's the likelihood, the probability that this is explained by a halo star, I would say, is much, much higher than this is explained by, I think. And so, I don't know. I was much less excited about it. I was very excited for 6 weeks. Ken knows this.
It's true.
Manuel, please.
Yes, so I am not a specialist, of course, in core collapse, okay? But I have a question, is, in fact, regarding this work of Sylvia. In some sense, I don't know that any model has considered that when you are in core collapse, you hit the star, and so you can generate these charge polarizations that increase the pressure, as Sylvia showed. And so you support the collapse, you create more mass, and after you collapse, because of course you lose that charge, okay, that is at the surface. And so, and even in your simulations of MHD, I would like to know if you have any electric field considerations there, okay? Because it's, for me, it's difficult to believe that the charge matter will remain neutral. Okay, it's, I don't know, it's hard to believe if you have gradient of temperatures, and so you know that this charge of 10 to 21 coulombs that you maybe realize that seems too big. Okay, it's only 1 part in 10 to 60 electrons. Okay, you have 10 to 76 electrons in a white dwarf. 10 to 21. Okay, if you divide by the charge of the electron, okay, is only, okay, like you can see, it's like 10 to 39, okay, so 10 to 40. So it's a very small difference on the charge, let's put neutrality. So, but, and so that's, okay, since I am not a specialist, okay, I'd like to know your opinion about this thing. If why you cannot consider some fluctuations on the charge in your charge neutrality in your simulations, and even in this charge collapse, because of course this could allow, okay, that you stop the collapse first, and after, of course, you collapse, so it will generate more energy. So I don't know. So maybe since I am out of the field, so maybe if you have any hint or any point about this that maybe is not possible, I would like to hear. I don't know. That's my point.
Seems Wolfgang has his hand up.
Just a very quick thing. I mean, make a prediction that is measurable and that would rule out your model. I think that's the way forward.
Yeah, the prediction is this. Okay, you have, it's of course Silvia didn't answer, but the prediction is already in the paper. You can get us to solar mass because you have this large pressure at the surface, and so you can.
But we don't measure surface pressure. Well, we do with log G, but I mean other models explain
because you do the energy when you got the energy that you release, of course, is related to that. Okay, and so and of course I didn't tell Sylvia to answer you, but you should test. Okay, put some electric.
No. You need to make the predictions, and then we can observe it.
No, but you can also do this thing, including in your codes of MHD. Okay, that you use. Okay. So,
that is not a prediction. That is not an observable.
No, it's a prediction because you can. No, you can predict maybe more energy release than you expected. No, I don't know.
Okay, I think thank you for those comments. I think we're almost coming up on our time. I just checked, Fritz, your paper with Sam. Is actually the manganese is quite high. It's almost looks like several hundred or perhaps even 1,000 times solar.
Yeah, I mean, of course, with the very high neutralization, you can probably also directly produce manganese, not over covert 55. There's probably YE goes low enough, right, so that you actually have a direct channel for manganese production there, I guess.
Yeah. Interesting. So we're almost at time. I think Pilar, you said we had 10 minutes or 15 minutes past our duration.
We still have 5 minutes until the end. If you want to comment about the last question, or you want to come back to one of the earliest questions, that's the moment.
Well,
I'd like to open the floor for folks to make final comments. You know, we'll have more time on Thursday, of course, but anything else that folks would like to say?
Well, maybe a general question about the super Chandrasekhar mass models. The misconception here is a little bit, I mean, people actually derive this thing with the super Chandrasekhar mass explosions based on the total emission in the optical, right? And the emission in the optical is only a tiny fraction compared to the energy that's released in the explosion. In the explosion, actually, you produce like 10 to the 50, close to some fraction of 10 to the 51 ergs. And in the optical emission, you release something like 10 to the 48 or something like that, right? Or in that order. It's a few orders of magnitude less. And now if you see a brighter type 1a supernova, that doesn't tell you that there must be a stronger explosion necessarily. It's just a question, and that is actually the alternative models, how you convert this explosion energy into optical emission in the end. There have been many models for that. And one is actually sort of that you have stuff around the exploding white dwarf and that you actually sort of then create the kinetic energy of the ejector by shock waves into emission. And that is actually one of the, I think, most plausible ways to explain these super bright type 1a supernovae. I mean, the thing is just that led to confusion that people in the beginning to make a big impact called these super Chandrasekhar mass explosions, but there is not necessarily any need to have a super Chandrasekhar mass white dwarf exploding there.
It's a very good point.
Thank you.
Before we are taken out, I would like to thank all the speakers. They have given extraordinary, wonderful talks. And also I want to thank to all the participants for the discussion. And I hope to see all of you on Thursday, but we can continue if you want.
Thanks to you for organizing this session. It was great to participate in it.
Thank you.
Thank you for joining us.
Thank you.
Thank you very much.
Thank you, everyone.
Bye.
Bye-bye.
Bye-bye.
Bye, everybody.